Hello, friend. Before anything else tonight, thank you for choosing this quiet corner of the internet to rest in. Wherever you're watching from, whatever kind of day chased you here, whatever thoughts are still buzzing around in the back of your mind, I hope the next few hours feel like something soft settling gently around your shoulders, the way a heavy blanket does on a cold night, pulling you slowly away from everything else. Tonight, we're going to talk about something that covers every square inch of your body right now as you listen to this. And yet you have probably never once stopped to think about it. Not your skin exactly. Something just beneath it quietly waiting for you to notice. You've probably spent your whole life believing you are the hairless primate, the one branch of the family tree that somehow shed its fur while every cousin kept theirs. But that belief is not quite true. In a quiet laboratory outside Boston, a team of scientists once laid a sliver of human skin beside a sliver of chimpanzee skin under a microscope and started counting. What they found took years to fully explain, and it rewrites the entire story of what actually happened to your body's fur. Tonight we go looking for the coat you were never told you still carry. Now, before we slip any further into tonight's story, let me say plainly what this is and what it is not. This is not a lecture. Nobody is testing you on any of this. Think of it more like a long, slow walk through some strange and oddly personal science meant to be listened to with your eyes growing heavy, not your notebook out. And if any part of what I bring you tonight settles into your chest the right way, a tap on that like button, a quiet subscribe, a comment left somewhere below costs you only a second, and it helps this little story find its way to somebody else who might need it too. While you're there, tell me something small. Where are you tonight? What city? What country? What corner of the world is holding you while you listen? I look through every single one you leave, and there is something quietly moving about, picturing all of you scattered across so many time zones, drifting towards sleep at the exact same story, just at different hours. Now, if you have not already, let the lights go soft. Maybe switch on a fan or something with a steady, gentle hum in the background, and let's begin. Over the next few hours, we're going to wander through some strange and honestly slightly unsettling corners of your own biology. Ancient parasites that quietly kept a record of history on their own bodies without meaning to. A theory about swimming apes that almost nobody in serious science still believes, and yet nobody has fully managed to bury either. A fact about your own birth that most people never learn, not once in 80 or 90 years of walking around on this earth. But before any of that, we have to start with the coat. The one hiding in plain sight right under the surface of your skin right now. Picture a laboratory on the edge of Boston, on an evening in 2018, long after most of the university has gone dark and still. Rows of empty desks, a single fluorescent light humming somewhere overhead. One office window is still lit, glowing faintly against the night outside where the last commuter trains are rattling home for the evening. Inside, an evolutionary geneticist named Yana Kambarov is bent over a microscope, working her way through a stack of glass slides that most people would find deeply unsettling to examine so directly. Slivers of skin. Human skin donated after death. Skin from 4 chimpanzees. Skin from 8 rhesus macaques, each one labelled catalogued and waiting patiently under the lens for its turn. Her team was chasing a question that sounds almost embarrassingly simple for a room full of Harvard researchers to be asking out loud. Do humans actually have fewer hairs than a chimpanzee? Or do we simply have the same number grown differently? Kambarov herself liked to point out something almost too obvious to say aloud. Anyone, she would explain, can glance at a person standing beside a chimpanzee and see immediately that their skin looks nothing alike. The far harder task, the one that had already swallowed years of her career, was explaining exactly why down at the level of one single follicle, one single gene quietly doing its work in the dark. So they counted. Forehead, back, chest, forearm, thigh. 5 separate regions of skin across 7 human donors, 4 chimpanzees and 8 macaques. every visible hair follicle marked and tallied under the lens, one patch of tissue at a time. And here is the part that quietly rearranges everything you thought you already understood. The count for humans and chimpanzees came back almost identical. Not roughly similar, almost identical. You were taught somewhere along the way that you belong to the naked branch of the primate family, the one that shed its fur entirely, but that is not what the follicles say. The follicles say you are still wearing nearly the same coat as your nearest living relative. It was never removed, it was only switched off. So the real question was never where your hair went. It was always why it stopped growing, without ever actually leaving. But the follicle count was only half of what Kambarov's team uncovered in that laboratory. Buried in the very same slivers of tissue sat something else entirely. Tiny coiled glands built for sweat. And when her team counted those instead, the story flipped completely. Humans, it turned out, carry something nearly 10 times greater in the number of these sweat glands than chimpanzees do, crammed into the exact same patches of skin where the hair follicles sit almost unchanged. The coat stayed. Quietly standing beside it in far greater numbers than anybody expected, sat a plumbing system built for something that coat was never designed to handle. We will spend a great deal of time on that plumbing system before tonight is through. For now, simply hold on to this one detail because it will matter later. Here is what is strange about the answer. Some researchers point to something as small as a single gene quietly deciding follicle by follicle to build a whisper of a strand instead of a thick one. Others think the change spread slowly, drifting across hundreds of thousands of years rather than flipping all at once. And the most careful scientist in that Boston laboratory will tell you quietly that the case is still in many ways wide open. Maybe it happened through one gene, maybe it happened through dozens working in slow coordination, or maybe, and this is the version that keeps evolutionary biologists up at night, the full answer is still sitting somewhere in a freezer full of skin samples waiting for somebody to notice it. Rewind further now, back to London in the 1960s. A young zoologist named Desmond Morris sits at his desk surrounded by notes on primate behaviour, working on a book with a title bold enough to scandalise half the country. He would call it simply The Naked Ape. His argument was almost insultingly direct. Stop studying human beings as though we exist somewhere outside the animal kingdom, he said. Study us exactly the way you would study any other primate species, and suddenly our bare skin stops looking like proof of some grand evolutionary promotion and starts looking like an unsolved biological puzzle instead. The book became one of the best-selling science titles of its decade, translated into dozens of languages, and it made a great many readers deeply uncomfortable in ways they could not quite put into words. Here is why. For a very long stretch of history, hairlessness had quietly been treated as a kind of upgrade. Proof that humans had climbed above the animals rather than simply change shape alongside them. Morris took that comforting idea and almost mischievously took it apart in public. There was no upgrade. There was only a switch somewhere in a strand of ancient genetic code that turned a thick coat into something almost too fine to see. And here is a small, quietly funny thought to sit with for a moment before we move on. Every time you notice a stray hair on your arm and reach for a razor or book a waxing appointment, or simply forget the whole thing exists until laundry day reminds you otherwise, you're in a very real sense negotiating with roughly 5 million hair follicles that never actually packed up and moved out. They just learned to whisper instead of shout. And this particular negotiation, it turns out, is nowhere near as modern as it feels. Walk back nearly 4,000 years to the households of ancient Egypt, and you would find women, and plenty of men too, mixing warm paste from honey or sugar and water, smoothing it onto their skin, then pulling it away in one motion, root and all. Others reach for pumice stones or tweezers carved patiently from seashells. Smooth hairless skin was not simply a preference back then. It stood for cleanliness, for status, for belonging to a household that could afford the time such rituals demanded. The wealthy of ancient Greece and Rome later borrowed the same habits, admiring skin that showed no trace of the coat underneath. So here is a small misconception worth setting down gently right at the start of tonight's story. This is not some invention of a modern beauty industry dreamed up in the last century to sell razors. Humans have been quietly waging this particular oddly intimate war against their own follicles for thousands of years in one form or another all across the world. Look closely enough at your own forearm under strong enough light and you will actually see it. Tiny, pale, almost transparent hairs catching the light at just the right angle, growing in the exact same pattern. A chimpanzee's fur would follow just impossibly fine, like frost on a window rather than fur on a body. Scientists call this vellus hair. Soft, short, barely pigmented, so easy to overlook that most people go their whole existence without ever noticing it is there at all. Only a handful of places on your body still grow the thick, darker strands called terminal hair: your scalp, your eyebrows. A few other regions the body seems to have deliberately chosen to protect. Almost everywhere else the follicle is still standing at its post doing exactly the job it always did. It has simply been instructed to build something small enough to disappear. Underneath each one of those follicles sits a tiny muscle so small it barely seems worth mentioning, called the erector pili. Its only task is to pull the hair upright whenever your body senses cold or fear or something sudden in the dark. You already know this feeling. You have felt it 1,000 times and probably never once had a name for it. We will come back to that small, stubborn muscle again later. It is still doing its ancient work faithfully even now, even with almost nothing left standing for it to lift. Notice it if you can the next time a cool breeze slips across your arms tonight, or a sound in the house makes you go still for half a second. That small tightening you feel is not new. It is one of the oldest reflexes your body owns quietly, rehearsing a performance it has not truly needed in a very long time. Now here is where the comparison turns truly strange, because humans did not simply drift away from the rest of the primate family on this. We walked an entirely separate road from every one of our closest cousins. Gorillas moving through the forests of Central Africa still wear the same thick, dark coat their ancestors wore 1,000,000 years ago. Orangutans high in the canopies of Borneo still carry that unmistakable curtain of long reddish hair. Even chimpanzees, our nearest relatives of all, kept their fur exactly where evolution first placed it. Out of an entire family of primates, one single branch quietly decided to keep every follicle in position, and switch nearly all of them down to almost nothing. That is not a small drift, the kind evolution produces almost by accident. That is a strange and rather dramatic decision made somewhere deep in your own ancestry, for reasons science is still working patiently to fully untangle. And it is worth sitting with for a moment just how unusual that makes you. Somewhere in the long chain of grandmothers and grandfathers stretching back millions of years, something happened to your family, and your family alone, that never happened to any of the others sharing that same branch of the tree. So here is where tonight's story truly begins. Not with an animal that lost its fur completely the way you might lose a jacket somewhere on a long trip and never see it again, but with an animal that kept every single follicle in place and simply stopped using most of them the way its ancestors once did. Why would evolution do something so strange? Why would a body hold on to 5 million tiny structures generation after generation, and then quietly instruct almost all of them to build something practically invisible? Some scientists will tell you it was about heat. Others will tell you it was about sweat or parasites or something as unexpected as attraction itself. A few will even take you somewhere stranger still toward an idea involving open water that most of their colleagues have spent decades trying and mostly failing to fully dismiss. By the end of our journey together over these next few hours, you will have heard every one of those theories weighed carefully against real research, real evidence, and real scientists who have spent entire careers chasing this one stubborn question, the very same question that first surfaced tonight standing quietly beside a microscope in that empty Boston laboratory. But there is a frustrating problem waiting for us at the very next step. Hair does not survive the way bone does. Skin does not survive the way stone does. Whatever truly happened to the bodies of your ancestors, it left behind no fossil to measure, no ancient skull to study under a light, nothing buried in the earth with the answer written plainly across it. Every other chapter of the human story leans on something solid. A jaw pulled carefully from a riverbank, a footprint pressed into ash that hardened before it could blow away, a tool chipped from stone still sharp enough to cut after millions of years underground. Fur leaves none of that. A body loses its coat, and within days, sometimes hours, every trace of it has rotted away completely, leaving scientists staring at bare, silent bone with no way of knowing what once covered it. So if the evidence was never buried in stone and never will be, where exactly has it been hiding quietly all this time, waiting for someone clever enough or strange enough to go looking in the right place? As it turns out, some of the most patient scientists on Earth found a way forward anyway in places nobody would ever think to check first. Not in a museum, not in a cave. In clues so small, so easy to dismiss, that it took real imagination just to start looking for them at all. That is where we go next. In May of 1952, brothers were cutting peat in a bog outside the Danish town of Silkeborg, doing work their family had done for generations, when a spade struck something that made both of them drop their tools and run for the nearest telephone. Whatever answer might exist to the question we ended on a moment ago, it was not waiting in a fossil bed or a stone tool or anywhere paleontologists usually think to dig. As it turns out, it was waiting somewhere far stranger than that. What Viggo and Emil Højgaard found buried beneath the peat looked at first glance exactly like a murder victim. A man's face curled gently on its side chin tucked toward his chest, eyes shut as if merely resting. Stubble still rough across his chin, eyelashes still resting against his cheek, each one distinct enough to count. A leather cap sat on his head, still buckled beneath the jaw, as though its owner had simply lain down for an afternoon nap in the mud. The local police were called, immediately certain they were looking at a recent crime, maybe even a name they already had on file. They were wrong by roughly 2,400 years. The man in the bog, now known simply as Tollen Man, had lived and died during the early Iron Age, hanged by a leather cord still knotted gently around his throat, then lowered into exactly the kind of ground that by pure chemical accident refuses to let a body rot the way bodies are supposed to rot. The acid in the peat, the near total absence of oxygen, a particular kind of moss that quietly tans skin the same way a tanner might cure leather. But between them, these conditions had done something that should, by every normal rule of biology, have been impossible. They had kept a human being's actual skin, actual hair, actual stubble intact for well over 2,000 years. Archaeologists who examined him afterward found no obvious wounds beyond the rope itself and no signs of a struggle. His stomach still held the remains of a final meal, a simple porridge made from dozens of different seeds and grains, the kind of humble Last Supper that hardly suggests a criminal facing punishment. Most researchers now believe he was not executed for any crime at all, but offered carefully and deliberately as a gift to gods, whose names have long since been forgotten, perhaps in exchange for a good harvest from the very land that ended up preserving him so faithfully. There is something almost tender in that thought, if you allow yourself to sit with it. The bog that took his life is the same bog that kept his face intact long enough for two brothers to stumble across it and briefly mistake an ancient offering for a modern crime. So here is a question worth sitting with for a moment. If human hair and skin can truly survive that long given the right conditions, why do we not have a single scrap of it from 3 million years ago, back when your ancestors were first beginning to lose their fur? To understand why it helps to know what decay actually is stripped down to its basic mechanics, the moment breathing stops, bacteria already living inside a body quietly and harmlessly stop being harmless. They begin consuming soft tissue almost immediately, and warmth speeds them up the way warmth speeds up almost every chemical process on Earth. Skin and hair are built largely from a tough fibrous protein called keratin, which sounds sturdy enough on paper, yet stands almost no chance once bacteria, insects, and simple moisture join forces against it. Bone survives far longer for a much simpler reason. Its mineral structure, built mostly from calcium and phosphate, has almost nothing in it that bacteria consider food. Given enough centuries underground, that same mineral structure can slowly swap itself out atom by atom for the surrounding rock, turning into something closer to stone than to living tissue. Skin never gets that particular privilege. It either survives intact through some rare accident of chemistry, or it disappears completely, usually within weeks. Half a world away and tens of thousands of years further back than any bog could ever reach, a very different kind of preservation had been quietly waiting inside the ice. In August of 2010, tusk hunters searching a stretch of coastline in northern Siberia came across a carcass sticking out of a frozen riverbank, its shape unmistakable, even half buried in silt. A young woolly mammoth, later named Yuka, lay curled on her side, much the way Tollund man had been, as though the ground itself kept borrowing the same peaceful sleeping posture. She'd been frozen for something nearly 40,000 years, and yet patches of her reddish-brown fur were still attached to her skin, strand by strand exactly where they had grown while she was alive. Later study would even find traces of brain tissue still sitting inside her skull, and fragments of genetic material so well preserved that researchers could examine molecules that should have crumbled to nothing tens of thousands of years earlier. Once again, biology had somehow refused to follow its own rules. Once again, the reason came down to chemistry and temperature working together at exactly the right moment. Permafrost, unlike a peat bog, does not merely slow decay down. Under the right conditions, it can stop that process almost entirely, holding a body inside a kind of frozen pause that can last tens of thousands of years without a single strand of fur so much as fading. It is worth remembering too that woolly mammoths themselves only vanished from the earth for good roughly 4,000 years ago, a small isolated population surviving on a remote island long after their mainland relatives had already disappeared. Compared to the age of your own species, that is barely any time at all. Now push the clock back further still, so far that comparing it to a mammoth barely makes sense anymore. On an afternoon in March of 2011, a heavy equipment operator named Sean Funk was clearing earth at an oil sands mine north of Fort McMurray in the Canadian province of Alberta, when his excavator bucket struck something far harder than the surrounding rock. Odd walnut-coloured lumps tumbled down the bank in front of him. He and his supervisor turned one over and found row after row of strange ringed discs patterned like nothing either man had ever come across in that mine before. Neither of them was a scientist. Neither of them expected on an ordinary Monday shift to be the first human beings in 110 million years to lay eyes on this particular creature's face. What Funk had accidentally unearthed turned out to be an armoured dinosaur later named Pelta that had died somewhere around 110 million years ago and washed out to sea, sinking to the muddy floor of an ancient ocean before anything could scavenge it. And astonishingly, its skin had survived the entire journey. Scientists studying the specimen could still make out its scales, its armour plating even faint traces of reddish-brown pigment running across its back, evidence of a camouflage pattern built to hide a slow plant-eating giant from predators. It had no hope of outrunning. Museum technicians would go on to spend more than 7,000 hours across nearly 6 years carefully freeing that skin from the surrounding stone without damaging a single scale. 110 million years. Sit with that number for a moment, then compare it to the far smaller handful of million years separating you from your own hairy ancestors. Something about that comparison starts to feel deeply unfair, which brings us to a fairly uncomfortable question, one that paleontologists studying human evolution quietly wrestle with every single day of their working lives. If a Cretaceous dinosaur can keep its skin for 110 million years buried under exactly the right kind of mud, and a mammoth can keep its fur for 40,000 years buried under exactly the right kind of ice, and a hanged man can keep his own eyelashes for 2,400 years buried under exactly the right kind of bog, then why does not a single early human ancestor anywhere across the entire African continent have so much as 1 square inch of preserved skin? The uncomfortable answer turns out to be geography. Your ancestors were not unlucky in how they died. They were unlucky in where they lived. Every one of those small miracles of preservation, the bog, the permafrost, the ocean floor, mud depends on one shared ingredient, an environment that keeps oxygen and bacteria away from a body almost the instant it dies. East Africa, where the earliest hominins spent millions of years walking upright across open, sun-baked ground, offers something nearly the exact opposite. Warm temperatures, plenty of oxygen, rivers that flood and recede with the seasons churning the ground instead of sealing it shut. Scavengers everywhere, from hyenas to vultures, to entire armies of insects, all more than willing to finish off anything soft long before it has any real chance of turning to stone. Think about it this way if it helps. A bog needs stillness and acid. A glacier needs permanent punishing cold. An ancient seafloor needs a sudden smothering blanket of fine mud, arriving faster than any scavenger could reach the body. The floodplains and savannas of the Rift Valley offer almost none of these things in almost any season. It is without exaggeration arguably the single worst possible landscape on the entire planet for keeping soft tissue intact across deep time. And it is exactly the landscape where your own species happen to spend the most important, most transformative stretch of its entire evolutionary story. There is a strange kind of comfort hiding inside that fact if you look at it from a certain angle. Somewhere right now in a museum drawer or a research collection sits a fossil hominin skull with a story written into every ridge and socket, a story about a face, a jaw, a way of chewing and moving through the world. What that skull cannot tell anyone, no matter how long they study it, is whether the person it belonged to shivered on a cold night the way you might tonight, or whether their skin caught the sun the way yours does. That silence is not a failure of science. It is simply the price of being born and dying in the wrong kind of dirt. So ask yourself something just for a moment before we move on. If every trace of your own skin and hair vanished within weeks of your death the way it would for almost anyone alive today, what would be left behind to explain who you were? A skeleton. Maybe a few objects buried alongside you, and nothing at all about the parts of you that felt warmth or cold, or a cool breeze against your arms on an ordinary evening. That is roughly the position paleontologists have been standing in for the entire history of their field, staring at bones and quietly wondering about everything the bones refuse to say. Bone can survive that kind of environment, slowly mineralizing over centuries into something nearing rock. Skin cannot. Hair cannot. In the specific unglamorous conditions where human evolution actually happened, soft tissue never once stood a chance. It is almost funny in a bleak sort of way once you sit with it long enough. The very landscape that shaped so much of what makes you human, the open plains, the endurance, the upright walk, the growing brain, is the exact same landscape that erased nearly every physical trace of the transformation as it happened. Have you ever stood in front of some ancient skeleton in a museum and quietly wondered what colour its eyes might have been, or how rough its skin would have felt under a fingertip? I have more times than I would probably like to admit. And for almost the entire history of paleontology, that particular question had no honest answer at all. Bones, teeth, the occasional stone tool, for a very long stretch of scientific history, that was the whole toolkit available. Long before anyone had genetics or even fully understood what a fossil actually was, one French naturalist proposed something that sounded almost like a magic trick. Working in Paris in the early 1800s, Georges Cuvier argued that every part of an animal's body stays quietly connected to every other part. Show him a single tooth, he claimed, and he could describe the general shape of the jaw. It came from the muscles that once moved it. Even something meaningful about the creature's whole way of life. Colleagues brought him fragments on purpose, half hoping to catch him guessing wrong. According to accounts passed down from his own students, he rarely did. His critics called this outrageous overreach, the kind of confidence no scientist should claim over such thin evidence. His admirers called it the birth of an entirely new way of interpreting the past. Cuvier could not, of course, actually see soft tissue preserved in a fossil. Nobody ever truly can. What he pioneered instead was something almost as valuable in the long run. The notion that absence itself can be studied carefully, methodically, almost like a language of its own. That a bone examined closely enough can quietly communicate real information about the flesh that once covered it, provided you know exactly how to interpret what it is telling you. That idea, more than 2 centuries old now, became the foundation for everything scientists would eventually use to chase down the mystery of your missing fur. Not fossils of hair, because none exist anywhere on Earth, and almost certainly never will. Instead, clues borrowed from entirely different places, from living creatures still walking round today, from molecules far too small for any eye to see, even strangely enough from a small parasite that never once stopped riding along on human skin, generation after generation, quietly keeping a kind of record nobody had thought to ask it for. It is a strange thought, honestly, that the answer to a question about your ancient ancestors might be sitting somewhere far more mundane and far more alive than a bog or a glacier or an ancient seafloor. Not preserved, not frozen, not fossilized at all, simply carried forward quietly generation after generation inside a creature small enough to overlook entirely riding along on human bodies, since long before anyone thought to wonder what it was keeping track of. That particular parasite, it turns out, was carrying something like a working clock ticking away on human bodies for far longer than anybody would have guessed, through empires and ice ages and everything in between, without a single person noticing it was there. And interpreting that clock correctly, once scientists finally thought to look, would eventually tell them something no bone, no bog, and no frozen mammoth ever could. That is where we go next. It lives on you right now, whether you like thinking about that or not, and it lived on every single one of your ancestors too, stretching back further than any fossil has ever managed to prove. A louse. Before you reach for the light switch, let me say this plainly. This is not going to be a chapter about infestation or itching, or anything designed to make your skin crawl on purpose. It is strangely enough one of the gentlest and most quietly brilliant detective stories in this entire field of science, and it starts with an insect. Most people spend their whole lives trying very hard not to think about it all. There is something almost poetic about that if you allow yourself to consider it for a moment. Of everything that might have survived to tell us the truth about your ancestors, it was not a grand monument or a beautifully carved tool or even a bone. It was one of the smallest, least dignified creatures on the planet, riding quietly along on human skin for longer than most nations have existed, keeping a kind of record nobody thought to ask it for until very recently. Here is the part almost nobody knows. Humans do not carry one kind of louse. We carry 2, and for a very long time scientists assumed they were simply the same tiny creature living in 2 different neighborhoods. The head louse spends its entire existence anchored to the hair on your scalp, gluing its eggs to individual strands near the warmth of your skin, usually somewhere near the nape of the neck or behind the ears where body heat sits thickest. The body louse looks almost identical under a microscope, similar enough that even trained entomologists once mistook one for the other. Yet it lives an entirely different life. It does not cling to hair at all. It lives inside clothing tucked into seams and waistbands and collars, only crawling onto skin long enough to feed before retreating back into the fabric, to hide mate and lay its eggs in the folds of a shirt or a blanket instead. That distinction sounds small. It is not. A body louse separated from clothing for more than a couple of days simply dies. It cannot lay eggs on smooth, bare skin. It cannot survive out in the open the way a flea or a tick might, hopping from host to host across bare ground. Its entire biology, its whole reason for existing in the particular shape it has, depends completely on one thing your ancestors did not always have: woven fabric to make its home inside. So here is a question worth turning over slowly, the way you might turn over a stone to see what is underneath. If body lice can only survive inside clothing, then body lice as a distinct kind of creature could not possibly have existed before clothing did. Which means somewhere buried inside the hereditary code of this small unglamorous parasite sits a rough date. Not for when your ancestors lost their fur, for something almost as interesting: the moment they finally covered up. In the early 2000s, at the Max Planck Institute for Evolutionary Anthropology in Leipzig, Germany, a researcher named Mark Stoneking became fascinated with exactly this question, alongside two colleagues Ralph Kittler and Manfred Kayser. Their plan sounded almost absurdly simple for a study that would end up reshaping an entire corner of human evolution. Collect lice from as many different corners of the world as they could manage, sequence their hereditary material, measure how long ago the head louse and the body louse split apart from a single shared ancestor, using the slow, steady tick of genetic mutation as a kind of natural stopwatch. They gathered around 40 lice from head and body populations scattered across the world, no small task in itself, since head and body lice look so similar that separating them correctly required careful attention to exactly where each specimen had been collected from on a willing volunteer. And for comparison, a louse taken from a chimpanzee, a distant cousin species that would let them calibrate their molecular clock against a known much older split between humans and chimpanzees themselves. Think of a molecular clock the way you might think of a river slowly wearing down a stone. Nobody watches it happen in real time, but measure how smooth and worn the stone has become, compare it to stones of known age worn by similar rivers, and you can work backward toward a reasonable estimate of how long the water has been flowing over it. Mutations accumulate in genetic material at a broadly steady, predictable pace, generation after generation, and researchers can use that steady drip of small changes the same way, provided they have something solid to calibrate their river against. 2 segments of genetic material from the tiny energy-producing structures inside each cell. 2 more segments from the main genome housed in the nucleus. Every sample painstakingly extracted, sequenced, compared letter by letter, and measured against the slow, steady rate at which small mutations accumulate across generations. The same basic principle a detective might use to date a fingerprint left decades ago if fingerprints changed slightly and predictably with every passing century. So here is a small question worth asking yourself honestly before we get to their answer. If someone handed you nothing but a handful of lice, no bones, no artifacts, no written record of any kind, would you have ever guessed you were holding a working clock? The number that came back startled even the researchers who had gone looking for it. Body lice appeared to have split away from head lice somewhere in the range of 70,000 years ago, give or take tens of thousands of years, either direction a wide but meaningfully useful window, carved out of deep time using nothing but a handful of insects most people would rather never look at directly. Other researchers were not satisfied with leaving the number quite that loose. A team led by David Reed at the University of Florida returned to the same question with a broader, more careful genetic analysis, drawing on additional samples and a wider stretch of genetic material, and pushed the estimate further back closer to 170,000 years ago. Their timing lined up with something else entirely. Something written not in insects, but in ancient climate records pulled from layers of ice and ocean sediment on the other side of the world. Roughly that far back, temperatures across much of the world had been sliding into an earlier brutal cold spell long before the more famous ice age most people picture when they hear that phrase. Regular clothing, it seemed, had not appeared out of simple convenience or vanity. It had appeared because staying bare in that particular stretch of history had started to mean freezing to death. There is a certain kind of logic hiding underneath that timing once you slow down and follow it through. Human populations at that point were still concentrated largely in and around Africa, much of it warm enough to make bare skin perfectly survivable. But climate does not stay still for anyone's convenience. As conditions cooled even in regions that had once been comfortable bodies, that had already spent the better part of 1,000,000 years shedding their natural insulation, suddenly needed a solution and needed it quickly. Clothing was not a luxury invented once humans had spare time to get creative. It was closer to an emergency patch stitched together out of necessity the moment a hairless body finally met a climate. It was no longer built to survive without help. Sit with that for a second, because it deserves more than a passing nod. 170,000 years ago, more or less, is the point where the genetic record says your ancestors began wrapping animal hides and woven material around their bodies with enough regularity that an entirely new species of insect had time to evolve around the habit. That same researcher, as it turns out, had already stumbled onto an even stranger piece of this puzzle a few years earlier, and it involves a completely different kind of louse altogether. Humans, uniquely among primates, carry not only head and body lice, but a separate, more distantly related species that lives almost exclusively in pubic hair. For years, biologists assumed humans had simply carried this parasite along since the earliest days of the primate family tree, the way chimpanzees have carried their own head louse for millions of years. Reed's team decided to test that assumption directly, comparing the genetic material of human pubic lice against lice collected from wild gorillas with considerable help from conservationists monitoring gorilla populations across Central Africa. The results surprised almost everyone involved. Human pubic lice turned out to be far more closely related to gorilla lice than to any louse living on a chimpanzee, our far closer evolutionary cousin, and the split between the two appeared to have happened only around 3 million years ago, long after humans and gorillas themselves had already gone their separate evolutionary ways. In other words, an ancestor of yours picked up this particular parasite directly from a gorilla, most likely through nothing stranger than sleeping in an abandoned nest or coming into contact with a carcass long after the two species had stopped being near relatives at all. Here is why that oddly specific fact matters for tonight's larger story. A parasite generally needs continuous unbroken habitat to make a successful jump like that and settle in permanently. If your ancestors had still been covered in a full unbroken coat of body fur at the time, this new parasite would have simply spread wherever it landed, the way head lice can wander across a fully furred body. Instead, it stayed confined almost entirely to one small separate island of hair. That strongly suggests the rest of the body was already nearly bare by that point, leaving pubic hair and head hair as two isolated patches cut off from each other by long stretches of nearly naked skin in between, each one eventually hosting its own separate species of unwelcome tenant. Now here comes the part that quietly rearranges the whole shape of this story. Other lines of genetic evidence gathered from an entirely different corner of human biology point to something far older. The genes responsible for skin pigmentation, the switches that darkened human skin, once thick body fur no longer shielded it from the sun, appear to trace back well over 1,000,000 years long before modern humans existed in anything like their current form, which leaves an uncomfortable, almost dizzying gap sitting right in the middle of your family history, somewhere nearing 1,000,000 years, give or take, during which your ancestors were already essentially hairless and had absolutely nothing to wear. Not primitive clothing, not crude wraps of leaves or bark tied loosely for a bit of shade, nothing at all. Picture that, if you can bear to, for just a moment. Bare skin walking upright across open grassland under a punishing equatorial sun for a length of time so vast it makes the entire span of recorded human history look like a single afternoon by comparison. Every sunrise meeting that same skin directly with nothing woven, nothing tanned, nothing draped over a shoulder to soften the blow. Every cold night on higher ground met the exact same way, with nothing but whatever warmth the body could generate on its own. No fur left to keep the chill away after dark. No fabric yet invented to take its place. Just skin alone doing a job it had only just finished learning how to do for a stretch of time longer than every human civilization that has ever existed laid end to end several times over. Have you ever wondered even for a moment what kept a body like that alive out there? Because it clearly was not insulation. Insulation was the very thing evolution had just taken away. That particular puzzle, the puzzle of how a nearly naked animal survived and even thrived for hundreds of thousands of years with no clothing whatsoever, turns out to have its own answer, and it has nothing to do with fabric at all. We will get to that answer shortly, and it involves something your own body is doing constantly right now without you ever noticing it. For now, though, there is something almost tender about sitting with these two lice so nearly identical to look at, so wildly different in what they reveal. One quietly proves that regular clothing is a relatively recent habit, younger than agriculture is old. The other, simply by existing at all in its current form, proves that your species spent an almost unimaginable stretch of time before that walking around in nothing but the skin it was born with. And in a strange roundabout way, these two tiny insects are still writing that same story today. Head lice have never really left. Nearly everyone has at some point spent an evening combing carefully through someone's hair with a fine-toothed comb under bright light, checking behind the ears the way people have checked for thousands of years without ever once thinking about where that particular ritual came from. Whoever did the combing that night took part, without realizing it, in a relationship between species that stretches back millions of years, long before either side looked anything like it does now. The parasite has not changed its habits nearly as much as its host has changed the world around it, so the fur disappeared first. The clothing came later as a patch of workaround stitched on top of a body that had already made its decision. Which leaves one final, rather large question hanging in the air before we move any further into tonight's story. If the coat was gone and there was nothing yet to replace it, what exactly was your body doing instead, all those hundreds of thousands of years to keep itself alive under an open sky? It could not have been luck. Luck does not stretch across hundreds of thousands of years, across countless generations in an environment that would have killed an unprotected body again and again if nothing else had been working quietly underneath the surface. Something else had to be carrying the weight that fur used to carry. Something already built into the skin itself, ready and waiting long before your ancestors ever thought to reach for a hide or a woven wrap. The answer was already there the entire time, quietly working, hidden just beneath the surface of the very skin we have been talking about all evening. It has nothing to do with fur and nothing to do with clothing. It has everything to do with water. That is where we go next. Water, it turns out, is not a metaphor here. It is the literal answer dripping quietly from somewhere between 2 and 5 million tiny openings scattered across your entire body right now. Whether you happen to be sweating this particular evening or not, every one of those openings belongs to something called an eccrine gland, and human skin carries a higher density of them than any other mammal on Earth. Not the highest among primates. The highest among every single mammal that has ever been measured, full stop. A chimpanzee has them too, scattered thinly across its body, but buried underneath a coat of fur that traps warm, damp air right against the skin the moment sweat tries to evaporate. A horse sweats technically, yet its sweat comes from an entirely different kind of gland, thicker and oilier, built more for a different purpose than pure cooling. And even then it has to work through a layer of fur, doing everything it can to hold that moisture in place instead of letting it lift away. Pound for pound, a horse's sweat manages to move far less heat off its body than yours does off of yours, despite the animal carrying vastly more muscle mass generating that heat in the first place. Your body abandoned that older system almost entirely. What replaced it is thin, watery, nearly odorless release directly onto bare skin with nothing standing between it and open air. It evaporates almost as fast as it appears, pulling heat away from the body with it over and over for as long as the supply of water holds out. A small handful of the older, oilier glands still linger in a few private corners of your body, mostly under the arms, mostly there for scent, rather than cooling a quiet leftover from the system your ancestors mostly abandoned. The physics behind this is almost embarrassingly simple once somebody explains it out loud. Evaporation only pulls heat away efficiently when moisture can actually lift off into open moving air. Trap that same moisture underneath a dense layer of fur and it simply sits there instead, soaking the skin, going nowhere, doing almost nothing useful. A furred animal essentially sweats into its own private greenhouse. A bare-skinned one sweats directly into the world. Strip the fur away first, and suddenly every drop of that same sweat starts working roughly twice as hard. Researchers studying mice have since traced part of this switch down to a single gene, one that appears to push developing skin toward building either a hair follicle or a sweat gland, but rarely both in the same patch at once. To turn that gene up and fur wins, turn it down and sweat glands multiply instead. Somewhere in your own deep ancestry, across an unimaginable number of small genetic adjustments, that particular dial seems to have been turned down patch of skin by patch of skin, until almost the entire body had swapped one system for the other. So here is where those two great mysteries we have been circling all evening finally meet. The fur disappeared, and in roughly the same stretch of deep time, this entirely new cooling system quietly took its place, spreading across the very same skin the fur used to cover. Have you ever wondered why humans sweat so heavily compared to almost every other creature on the planet, to the point where it can feel almost embarrassing on a hot afternoon? It is not a flaw in the design. It is in a very real sense the entire point. In 2004, two researchers named Dennis Bramble and Daniel Lieberman, one working out of the University of Utah, and the other at Harvard, published a paper that reframed this whole question in a way few people expected. For decades, most scientists studying human movement had quietly assumed that running played only a minor, almost accidental role in our evolutionary story, since humans are such poor sprinters compared to nearly every other mammal our size. Bramble and Lieberman looked at the same skeleton everyone else had been studying and asked a slightly different question. What if that hairless, heavily sweating body was never built primarily for walking at all? What if it was quietly, deliberately built to run and to keep running long after everything else on four legs had given up? Working from the skeleton outward, the two of them catalogued a long list of features that make far more sense as running equipment than walking equipment. A long springy tendon at the back of the heel, storing and releasing energy with every stride the way a walking gait never quite demands. An arch in the foot doing something similar. A short, thick ligament running along the back of the neck, found in horses, found in dogs, built for the chase and completely absent in chimpanzees, whose heads simply are not built to stay steady, while the whole body pounds rhythmically across open ground. A noticeably larger backside than any ape can claim, doing comparatively little work while walking, yet firing hard the instant a walk breaks into a run, helping to keep the whole trunk from pitching forward with each stride. Even the narrow human waist twisting gently against a wider set of hips with every step turns out to help the upper body counter-rotate smoothly, while the legs do the harder work below. None of these traits on their own proves very much. Stacked together, they look far less like coincidence and more like a blueprint, one that Bramble and Lieberman argued had been quietly written into the genus Homo somewhere around 2 million years ago. Here is the part that tends to surprise people most. Judged purely on top speed, humans lose almost every race worth naming. A cheetah, a horse, even a common backyard dog will leave a human sprinter behind within seconds. But stretch that same race out across an entire afternoon, particularly a hot one, and something remarkable starts to happen. Most four-legged runners are forced to slow from a gallop down to a trot once they overheat, since galloping and open-mouthed panting cannot physically happen at the same time. A human, meanwhile, keeps going. Breathing stays completely independent of stride. Sweat keeps pouring from millions of open glands with no fur in the way. Given enough distance and especially enough heat, a person on foot can outlast an animal that would have vanished over the horizon within the first few minutes. Few people have watched this play out in real life quite as closely as a South African researcher named Louis Liebenberg, who spent years documenting something called persistence hunting among small groups of hunters in the Kalahari Desert of southern Africa. In 2001, a tracker named Karoha Langwayne filmed for a nature documentary narrated by David Attenborough spent roughly 8 hours doing exactly what Bramble and Lieberman's skeleton had predicted his body could do. He picked out a single kudu from a herd, a large, powerful antelope more than capable of outrunning him in any short burst, and simply began to follow it. Not sprinting, trotting mile after mile through the hottest part of the day, temperatures climbing well above what most people would call comfortable, never letting the animal settle long enough in the shade to cool back down. Picture that landscape for a moment, since it matters. Flat sun-baked scrubland stretching out in every direction, heat shimmering visibly off the sand, almost no shade beyond the occasional thorn tree. A single man carrying only a handful of arrows and the simple wooden weapon needed to fire them, moving at a pace that looked to anyone watching almost too relaxed to be dangerous. The kudu could run circles around him early on. It had no reason yet to think of him as anything more than a minor irritation, a slow upright shape trailing somewhere behind. But every time it stopped to pant in whatever shade it could find, catching its breath in short, desperate bursts, Langwayne arrived again minutes later, forcing it back into motion before its body temperature had any real chance to drop. Hour after hour, the gap between predator and prey narrowed, not because the humans sped up, but because the animal's own cooling system was gradually failing it, one exhausted stop at a time. By the end of the chase, the kudu could barely stand, its body pushed well past what its fur and its panting could manage, while the man who had been quietly trailing it the entire time was still on his feet. That particular hunt has since been watched by millions of people online, most of them with no idea they were essentially watching a demonstration of Bramble and Lieberman's argument acted out in real time by a body built for exactly this purpose. Liebenberg himself, on an earlier hunt in the same region, learned this lesson the hard way from the opposite direction. Running alongside a group of Kalahari hunters chasing a kudu through midday heat that climbed well past body temperature, he pushed himself so hard that his own cooling system eventually failed him too, leaving him dangerously dehydrated by the time the animal finally went down. Even a body built for this work has its limits once the water supply itself runs short. So let's return for a moment to that uncomfortable stretch of prehistory we sat with a little earlier this evening, all those hundreds of thousands of years with no fur and no clothing yet invented to replace it. It turns out that the gap was never really empty. Something had already moved in to fill it, and that something was this: an entire body quietly rebuilt around the simple, relentless act of staying cool, while everything around it eventually could not. It came at a cost though, and it is worth naming honestly before we move on. A body sweating at full capacity can lose a startling amount of water in a single hour, water that has to be replaced from somewhere, or the whole system begins to fail exactly the way it failed Liebenberg out there on the sand. For whatever its downsides, never demanded that kind of constant refueling. A furred animal can walk away from water for a full day and barely notice the difference. Trading insulation for evaporation was not a purely generous upgrade handed down by evolution. It was closer to a bargain, one that solved the heat problem beautifully, while quietly opening up an entirely new problem involving water, and where on earth a body might reliably find enough of it day after day to keep the whole system running. There is something worth sitting with here if you allow yourself the moment. The very trait so many people quietly find embarrassing about their own bodies sweating through a shirt on a warm day was very possibly the single advantage that let your ancestors out-hunt animals stronger, faster, and better armed than they were in every other respect. Not through claws, not through speed, through simple, patient endurance and a cooling system no other creature on the savannah could fully match. Think about that the next time a summer afternoon leaves you reaching for a fan or peeling off a jacket. Would you have guessed before tonight that this particular inconvenience was once one of the most quietly effective hunting weapons your species ever carried, older by far than any spear or arrow? Oddly enough, you do not need to travel back to the Kalahari or back millions of years to see a small, slightly comic echo of this same advantage playing out even today. Since 1980, a tiny village in Wales called Llanrwtyd Wells has hosted something called the Man vs. Horse Marathon, a 22-mile race across hills and open moorland, pitting human runners directly against horses and their riders. For its first 24 years, a horse won every single time, exactly as almost anyone watching would have expected. Then in 2004, on an unusually warm day, a marathon runner named Hugh Lobb crossed the finish line in a time no horse that day could match. Researchers who later studied decades of results from that same small Welsh race noticed something Daniel Lieberman himself would later point to directly. Every single time a human had actually beaten a horse, over the full course, it happened on one of the hottest days in the event's history. Cooler, wetter years belonged reliably to the horses. The hot ones again and again told a slightly different story, one that a persistence hunter chasing a kudu across the Kalahari would have found entirely unsurprising. A pair of physiologists eventually pulled together decades of race results from that same Welsh course, along with data from two other long-standing human versus horse endurance events held in the United States, to test the pattern properly, rather than simply eyeballing it. Sure enough, both horses and humans slowed down as the weather warmed exactly as anyone would expect. But the horses slowed down noticeably faster. Every degree of added heat chipped away at the gap between them, a small, steady reminder that the advantage Bramble and Lieberman described in Ancient Bone was still quietly writing itself into modern race results, one warm Welsh afternoon at a time. None of this, though, quite explains why the process started in the first place. Evolution does not plan ahead. No ancient body decided in advance that giving up its fur would someday make for excellent hunting weather, or that a system built around water was worth the risk of running dry. Something in the immediate daily reality of that landscape had to make bare skin worth the risk, long before any of these advantages could ever pay off. So picture the earliest moment in this entire story, long before running, long before hunting, long before any of the advantages we have spent this evening admiring had any chance to matter at all. A creature covered in fur standing somewhere in a rapidly changing world facing heat, for reasons that had nothing to do with chasing anything. What was that world actually like? What had changed underneath its feet and above its head to make a full coat of fur suddenly feel less like protection and more like a burden? That particular piece of the puzzle takes us back to the ground itself, to the specific shape of the world your ancestors were actually standing on millions of years before any of them ever thought to chase anything at all. That is where we go next. Somewhere around 3 million years ago, the forests of East Africa began to lose an argument they had been winning for millions of years. Rainfall that had once kept the region a thick, unbroken canopy of green began arriving less reliably year after year, decade after decade, as the wider climate slowly cooled and dried. Trees that depended on that steady moisture began thinning out, retreating toward rivers and lake edges, giving up ground to something new. Grass. Vast, open, sun-scorched grassland spreading further each generation, until entire stretches of the landscape that had once been shaded canopy stood almost completely exposed to the sky. Try to imagine what that transition would have actually felt like, lived one lifetime at a time rather than observed from millions of years away. A young animal born into a forest still thick enough to hide in might have died decades later somewhere near the edge of open plain its own grandparents would barely have recognized. No single dramatic afternoon marked the change. Just a slow, patient erosion of shade generation, folding into generation until an entire way of life simply stopped being available anymore. Scientists have traced this shift through some surprisingly patient detective work examining ancient soil chemistry and fossilized pollen buried in layer after layer of sediment. each layer quietly recording which plants were thriving in a given stretch of centuries. Forest plants leave one particular chemical signature behind in ancient soil carbonate. Grassland plants leave another entirely different one. Researchers working in Kenya's Turkana Basin, among other sites scattered across East Africa, have pulled long unbroken columns of this evidence directly out of the ground, each column laid out almost like tree rings turned sideways across a much longer stretch of time. Read enough of these layers in order and you can watch almost like flipping through a very slow film, a canopy fading into open plain. For a creature built for life in dappled shade, this was not a small inconvenience. It was a complete change of address forced upon an entire lineage with no say in the matter at all. Here is where a British researcher named Peter Wheeler enters this story working out of Liverpool in the 1980s, with a question that sounds almost too simple for how far it would eventually reach. If your ancestors were suddenly stuck out in that open grassland under a sun with nowhere left to hide from it, what would that actually do to a body still covered head to toe in fur? Rather than guess, Wheeler decided to measure it in a way that feels almost charmingly low-tech next to the genetic laboratories we have spent much of this evening inside. He built a small-scale model posed to represent an early hominin, and set it up outdoors to track the sun's path across the sky over the course of a full day. Every 20 minutes or so, he stopped and photographed the model exactly as the sun itself would have seen it, treating his own camera lens as a stand-in for the blazing eye overhead, then measured how much surface area appeared exposed in each shot. He repeated the entire process twice, once with the model standing upright, once with it posed on all fours the way a chimpanzee actually moves through its world. The difference startled him. A model on all fours presenting its entire back to the midday sun absorbed roughly 60% more solar radiation than the exact same model standing upright with only the head and shoulders left facing that same overhead sun directly. Standing tall did something else too, something almost as useful. It lifted the rest of the body up into air that moved more freely a few feet off the baked ground, catching whatever's breeze existed instead of trapping still superheated air, the way a body low to the ground inevitably does. Even a gentle current of moving air barely worth noticing on an ordinary day can carry away meaningful amounts of heat once it reaches skin that is actually exposed to it rather than sealed away beneath a low ground-hugging posture. So here, according to Wheeler, was a tidy, elegant answer. Stand upright and you cut your solar heat load dramatically, almost automatically, without changing a single thing about your fur. Lose the fur on top of that, freeing up the sweat glands we spent the last part of this evening getting to know, and the body gains an extraordinarily efficient way to shed whatever heat still gets through. Two adaptations working together as a matched set purpose, built for exactly the landscape those retreating forests had left behind. There is a pleasing symmetry here worth pausing on, since it ties directly back to the endurance running story we sat with only a little earlier tonight. Bramble and Lieberman's entire argument about a body built to chase prey across open ground quietly assumes a body that already had somewhere to put all that heat. Wheeler's savanna, in a sense, is the stage that argument needed all along. Without an open, sun-blasted landscape pushing fur out of the equation, first, there would have been no bare, heavily sweating runner left standing at the end of a long hot chase in the first place. One idea explains the pressure. The other explains what the body did once that pressure had already reshaped it. Wheeler pushed the idea one step further into territory that connects to something almost every viewer watching this happens to be using right now. The human brain is a spectacularly heat-sensitive organ, consuming something nearing a fifth of the body's entire energy budget, despite being a fairly small fraction of its total weight. Overheat that organ even slightly, and its performance drops fast, the same way a laptop left in direct sun starts behaving strangely long before anything actually catches fire. Wheeler argued that the surplus cooling capacity created by standing upright and losing dense fur may have done more than simply keep early hominins comfortable. It may have quietly opened up the thermal headroom that eventually allowed a brain to grow larger than any other primate had ever managed to support. Have you ever wondered why so many animals with truly impressive bodies built for strength or speed far beyond anything a human could match still carry comparatively modest brains for their size? Heat may be a large part of that quiet limitation, a ceiling most species never had the particular cooling system needed to push past. For a couple of decades, this became something akin to the standard explanation taught in university lecture halls. Then in 2011, two researchers named Graham Ruxton and David Wilkinson decided to test it more rigorously and found a genuine complication Wheeler's original model had quietly left out. Standing still in the sun, they pointed out, is not the same thing as walking through it. Wheeler's elegant photographs had measured a stationary model calm and motionless against the sky. Real hominins foraging across real grassland were not standing still for hours at a stretch. They were walking, searching, working, and working muscle generates its own internal heat, layered directly on top of whatever heat the sun itself was contributing from above. Once Ruxton and Wilkinson built that extra self-generated heat into their calculations, using conditions modelled on a truly brutal equatorial day, air temperature reaching well past body heat itself, under a fierce midday sun, the advantage of upright posture alone shrank considerably. According to their revised numbers, it was specifically the loss of fur far more than the switch to standing tall that did the heavy lifting in keeping an active walking body from overheating. Have you ever noticed how a single missing variable in an otherwise reasonable idea can quietly change the entire conclusion? That is essentially what happened here, and to their credit, nobody involved simply dug in and defended the original version out of stubbornness. Science at its best behaves exactly the way it did in this particular case. Someone builds a careful model, someone else finds the piece it missed. The whole picture gets a little sharper, even if the new version is messier and less satisfying than the first. There is no dramatic villain in this story, no scientist proven foolish in front of the world. Only patient people decades apart, each adding one more careful layer to a question far too large for any single study to settle on its own. This refinement carried an unexpected consequence for the timeline of this entire story. If bare skin and not upright posture by itself was doing most of the real thermal work, then the earliest bipedal hominins walking upright millions of years before anything resembling a modern human existed may well have still been carrying a full thick coat of fur while they did it. Standing tall likely came first, driven by other pressures entirely. Pressures about energy, about food, about simple, efficient movement across long distances. Losing the fur came later as its own separate chapter tied specifically to a hotter, lower, more relentlessly exposed stretch of landscape that later members of the human family eventually pushed into. A follow-up study a few years later added one more layer of nuance worth mentioning, since it does not simply confirm the story so far, but quietly complicates it in an interesting direction. Researchers revisiting the exact altitude and elevation where early bipedal fossils have actually been recovered notice something Ruxton and Wilkinson's model had not fully accounted for either. Many of those early sites sit at a meaningfully higher, cooler elevation than the sweltering lowland savanna most people picture when they hear the word. Correcting for that altitude softened the heat problem considerably for those particular populations, suggesting fur loss likely waited even longer than the earlier revision proposed, arriving only once later. Hominins pushed down into the hotter lower ground where the genus Homo would eventually spend most of its time. Notice how neatly that particular detail lines up with something we sat with earlier this evening, back when we were talking about parasites and pigmentation genes, rather than sunlight and altitude. The genetic evidence pointed to skin already going bare somewhere over 1 million years ago, while clothing itself only entered the picture roughly 170,000 years back. a body that lost its fur specifically once it moved down into hot, low-lying, thoroughly exposed ground fits that older timeline surprisingly well, almost as though two entirely different kinds of evidence gathered by entirely different scientists using entirely different tools had quietly been describing the same event from two separate directions all along. Picture that for a moment, since it truly reshapes the whole mental image most people carry around of ancient human ancestors. Not a single sun-bronzed, hairless figure striding confidently across open grassland from the very beginning. Something closer to two separate creatures separated by a very long stretch of time, each one solving a different half of the same enormous problem. First, a furred upright walker already balanced on two legs for reasons that had nothing yet to do with heat. Still shaggy across the shoulders and back, still fundamentally an animal of the old forest edge learning to survive somewhere new. Later, much later, a descendant of that same walker finally shedding its coat once the landscape it called home became too hot, too open, too relentless for fur to make sense anymore. Stepping into something far closer to the bare, sweating body listening to this very sentence tonight. There is something almost humbling about watching a scientific idea evolve this way, layer by layer, correction by correction. The same way those ancient soil samples recorded one slow change after another. Wheeler was not wrong so much as incomplete, and the researchers who came after him were not so much proving him wrong as sharpening a picture that had always been a little blurrier than anyone first assumed. It is worth remembering that the next time any single explanation for something this old sounds a little too neat, a little too complete, the real story almost always turns out to have more chapters than the first version admits. None of this, though, actually explains how a body pulls off the trick of losing its fur in the first place at the level small enough to matter. Standing upright is a matter of bone and posture, something a skeleton can still whisper about millions of years later. Losing a coat that took tens of millions of years of primate evolution to build in the first place is a matter of something far smaller, written into instructions so tiny that no fossil, no ancient soil sample, no photograph of a scale model in the sun could ever hope to capture it directly. So where does an answer like that even come from when bones stay silent and soil can only tell you about plants? It comes from a place none of tonight's earlier detective work has taken us yet. Not a bog, not a glacier, not an ancient seafloor, not even the patient molecular clock ticking inside a parasite. Somewhere far stranger and considerably more surprising once you actually see where it takes you. Ask yourself honestly where you would even begin looking if bones and soil had already told you everything they were ever going to tell. Most people understandably would assume the trail simply runs cold at that point, that some questions about the deep past are destined to stay permanently unanswered. Scientists studying this particular mystery refused to accept that, and the place they eventually turned instead was not a place at all, but a method buried inside the shared code that every living creature on this planet still carries around inside itself. And here is where the story takes its strangest turn yet, because when scientists finally went looking for that answer, inside the genetic code itself, they did not find something unique to humans at all. They found the exact same signature quietly repeated in creatures that share almost nothing else with you whatsoever. Creatures the size of a small car, creatures that spend their entire lives in darkness underground, creatures that have not set foot on dry land in tens of millions of years. That is where we go next. Let me answer my own riddle before it sits too long in the dark. The creature the size of a small car is an elephant standing somewhere on the plains of Africa right now, wrinkled skin catching the last of the day's heat ears, working slowly back and forth like a pair of hand fans nobody ever needs to hold. The one that spends its entire existence in darkness underground is a small pink, almost alien-looking rodent called the naked mole rat, tunneling through the soil of East Africa in colonies that can number into the hundreds, Some individuals living for decades in a species where most rodents barely last a handful of years. And the one that has not touched dry land in tens of millions of years is a whale or a dolphin gliding through open ocean without the faintest memory, genetic or otherwise, of ever needing to stand on solid ground again. None of these animals has anything obvious in common with you. Different diets, different homes, different sizes so extreme that placing a human, an elephant, and a naked mole rat side by side feels almost like a joke rather than a scientific comparison. And yet every single one of them shares this one strange specific trait with you: almost no hair. Here's the question that should probably be keeping you a little more awake than a bedtime story usually intends. If hairlessness evolved completely independently in completely unrelated branches of the mammal family tree separated by tens of millions of years and entire oceans and continents, would you expect the underlying biology to look the same in each case or wildly different? Most working scientists going into this question expected wildly different. What they found instead, when they finally sat down and checked properly, was something closer to eerie. In 2022, 3 researchers named Amanda Kowalczyk, Maria Cecchina, and Nathan Clark, working across Carnegie Mellon University, the University of Pittsburgh, and the University of Utah, set out to compare the full genetic blueprints of 62 different mammal species side by side. Some of those species were thickly furred the way most mammals actually are. A handful were not. Elephants, rhinoceroses, naked mole rats, pigs, armadillos, walruses, manatees, dolphins and whales, and sitting quietly in the middle of that unusual lineup, humans. Try picturing that particular spreadsheet for a moment, since it captures something truly delightful about how this research actually works. Somewhere on a university server sat a single enormous file, treating a 2-ton elephant and a 5-pound naked mole rat, and an ordinary person scrolling through social media on their sofa as data points belonging to the exact same statistical category. No zoo, no ocean, no burrow could ever bring these animals together in one room. A shared genetic database did it without the slightest difficulty. Their tool of choice was a piece of software built specifically for this kind of question, capable of scanning roughly 20,000 genes and something nearing 350,000 smaller regulatory regions, the stretches of genetic code that do not build proteins directly, but instead control when and how strongly nearby genes switch on. Rather than looking for one single hairless gene the way earlier researchers might have gone looking for one single villain, this team was hunting for patterns. Places in the genome that had changed unusually fast over and over again, specifically in the lineages that had lost their hair, no matter how distantly related those lineages actually were to one another. By carefully mapping out the mammal family tree, the team could see that hairlessness of this kind had not evolved just once, quietly passed down through a single hairless ancestor. It had evolved independently at least 9 separate times. 9 entirely separate evolutionary experiments run by nature across tens of millions of years, on 9 completely different branches of the same enormous tree. So here is where the story gets quite honestly a little strange. Given 9 unrelated attempts at the exact same outcome, you might reasonably expect 9 unrelated genetic solutions, the biological equivalent of 9 different engineers, independently solving the same problem in 9 completely different ways. Instead, the team found roughly 20 specific genes, along with nearing 2,000 smaller regulatory regions, showing the exact same telltale signature of rapid repeated change across almost every one of these hairless lineages: elephant and human, naked mole rat and dolphin, species that have not shared a common ancestor in tens of millions of years, independently reaching for what amounts to the same small toolbox over and over again. Have you ever solved a puzzle only to compare notes with a total stranger later and discover they landed on the exact same unusual solution entirely on their own? That is roughly what evolution appears to have done here. except the strangers in question are separated not by a room, but by tens of millions of years and half the branches of the mammal family tree. Imagine explaining that particular coincidence to someone with no background in biology at all. Two creatures never once in contact, never sharing a single ancestor for tens of millions of years, quietly arriving at the same page of the same manual, purely because that manual only ever had so many useful pages to begin with. Among the genes that kept showing up again and again, one particular family stood out clearly above the rest: keratin. The very same tough fibrous protein we spent some time with earlier this evening, the literal building material hair itself is made from. It makes a certain kind of sense once you sit with it. If you are nature faced with the task of dialing down a body's hair coat, the genes that actually build the hair shaft are the most direct lever available to pull. 9 separate lineages chasing 9 separate reasons to lose their fur kept ending up at the same lever again and again, almost as though there were only ever a small handful of doors leading out of a furry body, and every one of these animals eventually found its way to roughly the same one. You do not actually need to travel to an ocean or a savanna to see a smaller, faster version of this same story play out. A handful of specific genes have already been linked to hairlessness far closer to home, inside a species most people know intimately. Certain hairless dog breeds owe their bare skin to a mutation in a single gene, also known to shape tooth development, which is why some of these dogs carry unusual irregular teeth alongside their smooth coats. A different hairless breed traces its condition to an entirely separate gene, involved in skin and hair follicle signaling unrelated to the first. 2 different dog breeds, 2 different genetic accidents, both landing on the same basic outcome through 2 completely different doors in that same small toolbox. Breeders selecting for an unusual look without knowing it were repeating in miniature over the span of a few centuries, an experiment nature had already run across the entire mammal family tree over tens of millions of years. There is something almost funny about that if you allow yourself to see it. Somewhere a breeder decades ago admiring an oddly smooth puppy in a litter and deciding to breed for that unusual trait had accidentally stumbled onto the exact same genetic neighborhood that elephants and whales and your own distant ancestors had already been quietly exploring for tens of millions of years. Nobody involved had the faintest idea they were repeating deep evolutionary history in a farmyard. The genome, it seems, does not particularly care whether the pressure pushing it toward bare skin comes from an ocean, a burrow, an open savanna, or simply a human being with a preference for an unusual-looking dog. Here is a detail worth sitting with for a moment because it connects directly back to something we noticed earlier tonight in an entirely different corner of this story. These genes were not deleted from the genome. Deletion would be the tidy storybook version of this process. Hair coding instructions simply erased and gone. What the researchers found instead looked more like an old machine quietly powered down rather than torn apart. The instructions for a full, thick coat of body hair are still sitting there, folded away inside your own genetic code at this very moment, and inside an elephant's, and inside a naked mole rat's, largely intact, but switched off exactly the way a light left unplugged still contains every wire it ever had. That detail alone should sound familiar by now. Your body did not remove its coat the way you might remove a piece of clothing and set it aside somewhere. It quietly stopped using the instructions to build one, while somehow managing to keep almost every single instruction on file, just in case buried where nobody but a careful geneticist would ever think to go looking for it. Does that thought sit strangely with you at all? Somewhere inside every cell in your body, folded away and unused, rests a complete set of blueprints for a coat of fur you will never actually grow. Not a metaphor. Not a rough approximation. An honest genetic record still there, still readable by scientists with the right tools, quietly waiting for a signal that for your entire lineage has not arrived in well over 1 million years. Ask yourself for a moment why evolution might prefer powering something down over tearing it out completely. Deleting a set of instructions, this deeply woven into the rest of the genome carries its own risks, a bit like ripping out an old wall in a house, without knowing exactly which pipes and wires happen to run through it. Switching something off quietly, gene by gene, leaves the option open to switch it back on again, someday should circumstances ever demand it, without having to reinvent an entire coat of fur completely from scratch. Now, an obvious question deserves an honest answer before we move any further tonight. If all 9 of these animals share such a similar genetic trick, does that mean they all lost their hair for the same underlying reason? It does not, and this is precisely where the story turns from strange back toward fascinating. An elephant did not need to chase prey across open grassland the way your own ancestors did. A naked mole rat has never once stood beneath a punishing equatorial sun. A dolphin has not needed to worry about overheating on dry land in longer than most mammal lineages have even existed. 9 species, 9 dramatically different lives driven by 9 dramatically different pressures. And yet when the moment finally came to shed their fur, nature appears to have reached into the exact same genetic toolbox each time, regardless of which problem it happened to be solving. Think about how strange that actually is for a second before we move past it. An elephant loses its hair partly because a body that large struggles to get rid of heat fast enough. Not because it needs to lose heat quickly like a runner, but because its sheer bulk barely lets heat escape at all. A dolphin loses its hair because water conducts heat away from a body so efficiently that fur becomes almost pointless, replaced instead by a thick layer of fat working underneath the skin. A naked mole rat loses its hair partly because underground tunnels stay at a remarkably steady temperature year-round, making a heavy coat an unnecessary weight to drag through narrow passages, and partly because bare skin turns out to be exceptionally good at feeling its way through total darkness. 3 animals, 3 almost opposite reasons, 1 shared genetic doorway. There is something worth carrying with you out of this particular corner of tonight's story, something closer to a small quiet lesson than a simple fact. Evolution is often described as endlessly creative, endlessly inventive, capable of producing wings and fins and hands from the same basic starting material given enough time, and that is true. But it is also in its own way deeply economical. Given a problem it has already half solved once in some completely unrelated species, millions of years earlier nature seems perfectly willing to solve it again, using the exact same tools, sitting right there in the shared genetic inheritance every mammal on Earth still carries, whether that mammal happens to reside in a desert, an ocean, or underground in total darkness. Somewhere in that thought sits a strange kind of comfort if you let it settle for a moment. You're not some unique biological accident standing entirely alone in how your body chose to solve this particular problem. You're one entry on a fairly short list joined by a 2-ton mammal built for stomping across grassland and a small pink creature that spends its whole life somewhere no sunlight has ever reached. Different lives, different centuries, different corners of the planet entirely and yet quietly. The exact same page of the same old instruction manual opened up 9 separate times. There is a particular kind of humility worth taking from that one that has nothing to do with feeling small and everything to do with feeling connected. Every time you catch a cold or notice a scar slowly fading, or watch a bruise change colour over a week, you're watching machinery that traces back through an unbroken chain to the exact same distant ancestor every other mammal on this list eventually branched away from. The hairless coincidence we spent tonight examining is simply one especially visible thread in a much larger, much older fabric, one that quietly ties an elephant, a dolphin, a naked mole rat, and the person listening to this sentence together far more closely than any of them would ever guess just by looking at one another. So why then did an elephant need to solve this particular problem at all? What could possibly connect an animal the size of a small car to a landscape that on the surface has almost nothing in common with the open grassland your own ancestors were once learning to survive on? The answer turns out to hinge on something almost embarrassingly simple, a basic rule of geometry that applies just as strictly to a 2-ton animal as it does to the tiniest mammal alive, and once you hear it, you will likely never look at an elephant's ears quite the same way again. That is where we go next. In 1926, a British scientist named John Burdon Sanderson Haldane sat down and wrote one of the strangest, most quietly brilliant essays in the entire history of biology, and he opened it with an image most people never quite forget once they have heard it. Haldane was by any measure an unusual character to be delivering a lesson about bodies and scale. A geneticist, a statistician, a man who had served in the trenches during the First World War and would later famously claim he enjoyed the sensation of being shot at. He wrote with a dry, almost mischievous wit rarely found in scientific writing before or since. The essay in question, tucked away among his other collected pieces, was barely 6 pages long, and yet it managed to explain something about the shape of nearly every living creature on the planet, using little more than plain language and a handful of everyday examples. Drop a mouse down a 1,000-yard mineshaft, he wrote, and provided the ground below is reasonably soft, it will land, shake itself off, and simply walk away. Drop a rat from the same height and it dies. Drop a man and his bones break. Drop a horse, and Haldane, with that same dry sense of humour that has outlived him by nearly a century, now simply noted that it splashes. Why would the exact same fall treat 4 different animals so differently? Haldane's answer had nothing to do with luck, and everything to do with a piece of basic geometry. Most people forget the moment they leave school. Shrink an animal's height, width, and length each by a factor of 10, and its weight drops to 1,000th of what it used to be. Its surface area, though, only drops to 100th. Weight falls away far faster than surface does, which means a small body has comparatively enormous surface area relative to how much of it there actually is to move, slowing its fall through the air enough to survive impacts that would shatter something built on a larger scale entirely. Think of it if numbers alone feel slippery in terms of a simple kitchen comparison instead. A single ice cube dropped into a warm drink melts within a minute or two, its cold spreading out fast because so much of it touches the liquid around it at once. Freeze that exact same amount of water into one solid block instead, and it lingers stubbornly at the bottom of the glass long after the cube would have vanished completely, simply because a large block hides far more of its volume away from the surrounding warmth. Bodies work along strikingly similar lines, whether the substance in question happens to be ice or living muscle, quietly generating heat with every beat of a heart. That same simple piece of geometry, it turns out, governs a great deal more than falling speed or melting ice. It governs heat. Here's where this story bends back toward the coat we have spent this entire evening trying to understand. Picture an animal as a rough sphere for a moment, since the underlying mathematics barely cares about the details of its actual shape. As that sphere grows larger, its interior volume, the part of it generating metabolic heat every single second simply by being alive, increases far faster than its outer surface, the only part of it actually capable of releasing that heat back into the world. A small animal is, geometrically speaking, almost entirely surface with barely any bulk hiding underneath. A very large animal is nearly the opposite. Enormous bulk quietly generating heat around the clock, wrapped in a comparatively modest amount of skin, struggling to let any of it escape. Have you ever wondered why the largest land animals on Earth tend to make their homes in places that are not actually the coldest available to them? Their real danger was never staying warm. It was the opposite problem entirely. Consider an elephant for a moment, since nothing illustrates this principle quite as vividly. An adult African elephant can weigh well past 6 tons, an absolutely staggering volume of living tissue every gram of it, quietly producing heat as a simple side effect of muscles working and organs functioning. Scale that heat production up against a comparatively modest amount of outer skin, and you get an animal permanently at risk of overheating simply by standing still and existing long before it has taken a single step. And yet, remarkably, an elephant carries no meaningfully functional sweat glands anywhere on its body. None of the 2 to 5 million tiny openings you yourself carry the ones we spent considerable time with earlier tonight. So how does an animal that large avoid slowly cooking itself alive under the African sun? The answer sits quite literally on either side of its head. An elephant's ears are not simply for hearing. Stretching out to nearly 6 feet across on some African elephants, they are threaded with an extraordinarily dense network of blood vessels running just beneath a layer of skin barely 1 to 2 millimeters thick, by far the thinnest skin found anywhere on the animal's entire body. Warm blood from deep inside that enormous body gets pumped out into this thin, richly vascular tissue, where heat can radiate almost directly into open air, cooled further by any passing breeze, before flowing back toward the core noticeably cooler than when it left. Researchers using thermal imaging cameras have measured blood returning from an elephant's ears at temperatures several degrees lower than when it departed, and some estimates suggest an elephant can cycle its entire blood supply through this improvised radiator system in under half an hour. Would you have guessed before tonight that Nia could do the job of an entire cooling system given enough surface area and the right plumbing behind it? That distinctive slow flapping you have probably watched in wildlife footage without thinking twice about it is not idle habit. It is active engineering stirring air across that thin blood-rich skin to speed up exactly the kind of heat loss an elephant's enormous body cannot otherwise manage on its own. Zookeepers and field researchers alike have long noticed elephants angling those same ears toward whatever breeze happens to be available, turning the whole animal in effect into a slow, deliberate weather vane built entirely around staying cool. So here at last is the elephant's version of losing its fur, and notice how different the underlying logic is from everything we spent the earlier part of this evening exploring. Your ancestors shed their coat, at least according to the evidence we've sat with tonight, largely to unlock a system built around movement chasing prey across open ground, under a punishing sun sweating steadily while doing something. An elephant sheds its coat simply by virtue of existing at the scale it exists, at whether it moves a single step that day or not. One hairless body evolved around action, the other evolved around sheer unavoidable geometry. Rhinoceroses and hippopotamuses face a milder version of this identical problem, carrying enormous bulk on comparatively modest surface area, and each has settled on its own particular workaround. A hippo spends the overwhelming majority of daylight hours submerged in rivers and mud wallows, using water itself as the cooling system. Its own skin cannot fully provide, occasionally exuding a thick reddish secretion across its skin that functions as a kind of built-in sunscreen for an animal whose exposed hide would otherwise burn badly under direct sun. A rhinoceros rolls in mud for closely related reasons, coating itself in a natural barrier against both sunburn and the swarms of biting insects that plague any large, thinly covered mammal standing in open country. Neither animal solved its heat problem by growing a more sophisticated version of sweat. Both simply borrowed a cooling system from the environment around them instead. Water and mud doing the job, their own skin was never quite built to finish alone. Here is a small, honestly rather funny question worth sitting with for a moment. If you had to guess before tonight which animal actually has the more sophisticated cooling system, an athletic human chasing prey across open grassland, or a 6-ton elephant standing perfectly still in the shade, which would you have picked? Most people understandably would guess the elephant simply because of its size, the same way most people would probably bet on the horse in that mineshaft thought experiment purely out of instinct. The truth in both cases runs the opposite direction. Your body dripping quietly from millions of active glands is doing something considerably more advanced than what even the most elegant elephant ear can manage through blood vessels and moving air alone. Size, it turns out, is not the same thing as sophistication, whether the question involves falling safely or simply staying cool. And this is precisely the detail worth carrying forward as tonight's story continues. Humans are not elephants, not remotely in the strict geometric sense Haldane was describing. An adult human, no matter how tall, no matter how broad, shouldered, sits nowhere near the scale at which body size alone would force fur into becoming a liability. If pure geometry were the whole explanation for your own bare skin, you would expect nakedness to show up reliably in every land mammal built on a roughly human-sized frame, and it simply does not. Deer keep their coats, wolves keep theirs. Large cats, kangaroos, black bears, even gorillas built noticeably larger and heavier than you kept every inch of their fur, too. Whatever list nature was working from when it decided which mammals could safely go without insulation body size similar to your own, clearly was not on its own enough to earn a place on it. So whatever pushed your own ancestors toward losing theirs, it clearly was not the same passive, unavoidable mathematics governing an elephant's ears or a rhinoceros rolling through mud. Something else had to be doing the work, something tied specifically to what your ancestors were actually doing with those newly bare bodies day after day under that same unforgiving sun. Picture for a moment an entire imaginary savanna crowded with every hairless mammal we have met tonight standing side by side in the same stretch of grassland. An elephant bare because its own bulk left it no real alternative. A rhinoceros bare for much the same reason patched over with mud. And somewhere among them a comparatively small upright sweating primate bare, not because its size demanded it, but because bare skin happened to serve a plan already well underway, a plan involving long chases, hot afternoons, and a cooling system built around movement rather than mass. 3 very different animals standing in the exact same imagined field, each one having arrived at nakedness by walking down a completely different road. There is something almost poetic sitting inside that contrast if you think back to the genetic detective work we spent time with only a little earlier tonight. An elephant and a human, remember, appear to have reached for the exact same small handful of genes when the moment came to switch off their own fur, the same keratin machinery quietly powered down in both lineages independently. And yet here, standing on opposite ends of the very same genetic doorway, are 2 animals that walk through it for entirely opposite reasons. One had no real choice in the matter, its own bulk making thick insulation a slow, quiet liability the moment it stood in open sun. The other chose bare skin in an evolutionary sense as a tool sharpened specifically for chasing something across that same open ground. Same door, same lock even. 2 completely different reasons for ever wanting to walk through it. Nature rarely offers just one route to the same rough destination. Sometimes a body loses its coat simply because its own size leaves it no other choice. Heat trapped inside, faster than thin skin, and a modest surface can ever hope to release it. And sometimes, as we have spent several hours now exploring together, a body loses its coat for the opposite reason entirely. Not because it was forced to by its own bulk, but because doing so unlocked an active advantage worth chasing on purpose, mile after hot mile across landscape after landscape. Both are true stories, both are documented careful patient science, and neither one on its own fully explains everything sitting underneath your own skin tonight. Reduce this entire evening down to a single tidy sentence, and you lose something important every single time. The real answer, the honest one, keeps insisting on having more than one chapter. The same way an elephant's ear and a marathon runner's shirt soaked through on a summer afternoon both quietly point back toward the exact same handful of ancient genes without ever once agreeing on why those genes mattered. Before we move any further, there is one more explanation worth placing honestly on the table, if only because so many people have heard some version of it, usually second-hand, usually treated with far more confidence than the actual evidence really supports. It involves neither open grassland nor elephant ears. It involves water, open water, and a particular kind of story about your ancestors that a great many working scientists find almost impossible to take at face value and yet cannot entirely dismiss either, no matter how many times they have tried. It is the kind of idea that shows up again and again in casual conversation, in documentaries, in half-remembered facts passed along, at dinner tables usually stated with far more certainty than the science underneath it actually deserves. Tonight we give it a fair hearing, the same careful patient treatment we have given every other theory sitting alongside it. Not dismissed outright, not accepted uncritically either, simply examined honestly the way any claim this old and this strange deserves to be. That is where we go next. A young marine biologist named Alistair Hardy was sitting with a book one evening in 1930, working through a chapter about human anatomy, written by an anatomist named Frederick Wood Jones, when a single stray observation stopped him cold. Humans, unlike almost every other land mammal on Earth, carry a distinct layer of fat directly beneath the skin itself, rather than packed away deeper around the organs the way it sits in a dog, a horse, or a chimpanzee. Wood Jones had simply noted the fact and moved on, treating it as one curious detail among many. Hardy, who spent his working life studying life in the ocean, rather than life on land, could not move on quite so easily. He recognized that particular layout instantly. It was the same basic arrangement found in whales, in seals, in almost every creature that spends its life submerged in cold water, insulated by a soft padding of blubber sitting just beneath bare skin. He set the book down by his own later account and simply sat with the thought for a while, turning it over the way you might turn over an unusual shell found somewhere it had no business being. An idea took hold of him that evening, and it would not let go for the next 3 decades. What if Hardy found himself wondering human ancestors had once passed through a stretch of their history spent wading, swimming and foraging along ancient shorelines, rather than moving directly from forest canopy to open grassland the way most of his colleagues assumed? What if the fat beneath your own skin at this very moment was not some strange evolutionary accident, but a quiet inherited memory of water? Hardy kept the idea almost entirely to himself. He was a respected young academic building a career in an unrelated corner of biology, and colleagues he trusted enough to mention it to warn him plainly that voicing something this unconventional could seriously damage his professional standing. So he waited. He built his career studying plankton, instead invented an instrument still used today to track ocean life across entire shipping routes, and only once he'd become a fully established, respected professor near the end of his working life did he finally decide the idea deserved to see daylight. On the 5th of March 1960, Hardy stood up in front of a rather unlikely audience, a gathering of the British Sub-Aqua Club in Brighton, and tentatively laid out what he called aquatic man past, present and future. He expected, by his own later account, a polite, mild reception from a room full of recreational scuba divers, an audience unlikely to raise much fuss over a speculative afternoon talk. What he got instead was national headlines within days, most of them badly overstating and oversimplifying what he had actually proposed, turning a careful, hedged suggestion into something closer to a tabloid announcement. Startled and more than a little embarrassed, Hardy rushed a clarifying article into print less than 2 weeks later in the magazine New Scientist under the title "Was Man More Aquatic in the Past?" Here is roughly what Hardy actually argued, stripped of the tabloid exaggeration that first carried his name into public conversation. Somewhere in the deep past, a branch of ancestral apes pushed out of shrinking forests by competition for food found themselves foraging along tropical coastlines, instead wading into shallow water after shellfish, sea urchins and whatever else the shoreline offered. Over time, according to Hardy, this partly aquatic lifestyle left its mark. Fat settled beneath the skin rather than round the organs, exactly as it does in marine mammals. Hair thinned out across most of the body, reducing drag through water, the same way it does for a seal or a dolphin. The body itself grew leaner and more streamlined than a typical ape's, better suited to slipping through water than lumbering across open ground. Does any of that sound at all familiar by now after everything else we have covered together this evening? It should, and that is precisely why this particular idea refuses to fully disappear, no matter how many times mainstream researchers have tried to shut the book on it. Hairless skin, a body built differently from a typical land mammal's. These are exactly the puzzles this whole night has been quietly circling from the very first moment we began. Hardy was not inventing a mystery out of nothing. He was offering his own answer to a mystery every single theory tonight has been wrestling with in its own way, and in fairness to him, he never claimed the answer was certain. Even in his own clarifying article, he was careful to frame the whole idea as a speculation, a word he used deliberately, well aware of how far it strayed from the accepted picture of his time. The idea might have stayed a small, mostly forgotten footnote in the history of science, if not for a Welsh writer named Elaine Morgan, who encountered it years later and found something in it that resonated far beyond fat distribution and hair density. In 1972, Morgan published a book called The Descent of Woman, and she used Hardy's aquatic idea as a direct challenge to what she saw as a deeply one-sided version of the human story then dominating popular science. One built almost entirely around aggressive hunting men, chasing prey across open plains, while women stood quietly at the margins of their own evolutionary history. Morgan imagined something different. Women and children wading safely along calm shorelines, gathering shellfish, developing bipedal walking not to chase anything, but simply to keep their heads above shallow water. Morgan had no formal scientific training, a factor critics repeated often and pointedly, and she wrote with a wit and lightness rarely found in academic writing of the period, once explaining that she wanted the book to be truly enjoyable rather than dense and forbidding. What she had instead of a laboratory or a research post was a gift for narrative, and her book found an enormous devoted general readership, even as professional anthropologists largely declined to engage with it at all. Later, in 1982, she returned to the subject with an entire book titled simply The Aquatic Ape, hoping a more thorough evidence-focused treatment might finally win over the scientists who had mostly stayed silent the first time around. It did not. The silence, if anything, continued largely unbroken. Have you noticed across tonight's journey together how often a good story and a well-supported theory turn out to be two entirely separate things? This particular idea sits right at that uncomfortable intersection, and it deserves to be examined honestly from both directions before we move on. It is tempting, especially late at night, with the lights down low, to simply pick whichever explanation feels the most beautiful, and let the evidence sort itself out afterward. Good science rarely allows for that particular comfort, no matter how appealing the alternative might sound. Here is where the story took an unexpected modern turn. In 2016, the beloved broadcaster David Attenborough, whose voice has narrated more hours of natural history than perhaps any person alive, spoke sympathetically about the aquatic idea during a radio series, giving it a level of public credibility it had rarely enjoyed within scientific circles for more than 50 years. Two working anthropologists, Alice Roberts and Mark Maslin, felt compelled to respond in print almost immediately, gently but firmly, laying out why the professional consensus still did not, and likely could not, support the theory as originally framed. Their response was respectful rather than dismissive, careful to acknowledge Attenborough's enormous public trust, while still insisting politely but plainly that trust in a beloved voice is not the same thing as evidence. Their objections, and the objections of researchers before them, come down to a few truly serious problems, not simply professional stubbornness or an unwillingness to consider anything unconventional. The fossil record itself leaves remarkably little room for a semi-aquatic chapter of this kind. By roughly 3,600,000 years ago, early hominins were already leaving unmistakably bipedal footprints dry upright and unmistakably adapted to walking on solid ground, in ash fields far from any coastline. The timeline researchers have carefully reconstructed simply does not have an obvious gap wide enough to comfortably fit the kind of extended aquatic detour Hardy originally proposed. Compare the bodies of those same early ancestors against Hardy's specific predictions, and the fit grows weaker still. He expected a face reshaped around swimming a long protruding nose, built to keep water out while the head stayed partly submerged. The fossils show nothing resembling that. He expected proportionally long streamlined legs built for kicking through water. Early hominin leg bones show nothing of the sort either. Perhaps most tellingly of all, compare a human body honestly against animals that are without any argument or asterisk fully aquatic. A seal has webbed limbs built specifically for propulsion through water. A dolphin's nostrils have migrated to the top of its head, sealed by a muscular flap the instant it dives. Manatees and whales carry blubber layers many times thicker than the modest padding sitting beneath your own skin built to survive in water that would otherwise pull heat from a body far faster than air ever could. A sea otter spending most of its life floating on its back in cold coastal water still keeps an extraordinarily dense coat of fur trapping a layer of insulating air against its skin rather than losing it direct proof that water alone does not automatically push evolution toward hairlessness the way Hardy assumed. Humans have none of the more dramatic adaptations on this list. No webbing beyond the faintest hint between your fingers, present in plenty of thoroughly landbound mammals too. No modified nostrils, no true blubber, only an ordinary comparatively thin layer of fat that plenty of purely terrestrial mammals carry as well, for reasons having nothing whatsoever to do with swimming. So where does that honestly leave us? Not in fairness at a simple tidy dismissal. A smaller, more careful version of Hardy's original idea does still receive occasional serious attention from a handful of researchers, one that drops the dramatic language of aquatic apes almost entirely, and instead asks a much more modest question. Did certain hominin populations at certain points spend enough time foraging along lake shores and coastlines for shellfish and other easily gathered food to leave some subtle mark on the body without ever requiring anything near a fully aquatic lifestyle? That gentler question remains open, debated quietly at the edges of the field, entirely separate from the far bolder claims that made Hardy's name famous and Morgan's books beloved in the first place. It is worth noting too that shellfish and other shoreline foods are unusually rich in exactly the kind of fats brain tissue needs to grow and function, which keeps this milder version of the idea from being dismissed quite as completely as its bolder ancestor. A number of serious researchers studying the deep history of the human diet have pointed to coastal and lakeside foraging as a plausible, well-evident source of those particular nutrients, entirely apart from any claim about swimming, diving, or hairlessness itself. The waterside and the aquatic ape are in that sense cousins rather than twins, one resting on reasonably solid dietary evidence, the other resting mostly on resemblance and hope. There is a small, honest lesson worth sitting with here before we move any further tonight. A theory can feel emotionally satisfying, can even carry real cultural and political value. The way Morgan's challenge to a male-centered origin story clearly did for an enormous number of readers, without that same theory being well supported by the physical evidence itself. Both things can be true simultaneously. Hardy noticed something real and worth noticing, that odd, distinctly unape-like layer of fat beneath your own skin. He simply may have reached for the wrong explanation to account for it, one considerably more dramatic than the evidence examined honestly actually supports. Set this particular idea beside everything else we've gathered so far tonight, and an interesting pattern starts to emerge. The Savannah story held up reasonably well under careful testing, though it needed real correction along the way. The endurance running story held up remarkably well, backed by skeletons, by modern hunters, even by a peculiar little race in the Welsh countryside. The elephant story held up because basic geometry rarely lies. The aquatic story, for all its charm, simply keeps failing the same tests again and again, decade after decade, no matter how many devoted readers have wanted it to succeed. Not every appealing idea about your own deep past turns out to be a true one, and tonight has quietly been teaching you how to tell the difference. One careful theory at a time, the same patient, unglamorous work. Every scientist we've met this evening had to do before arriving anywhere near a real answer. So if it was never really about water, what was that fat actually doing there in the first place, quietly padding a body that had already given up its fur for reasons that by now have very little to do with swimming, and a great deal more to do with something considerably more intimate? Something involving attraction itself, and a question about your own skin that has nothing to do with heat at all. Think for a moment about everything bare skin actually reveals that fur once quietly hid away. Every blemish, every scar, every faint sign of illness or parasite visible now in a way it never could have been underneath a full concealing coat. That particular consequence of losing your fur, mostly overlooked so far tonight, turns out to have its own passionate group of defenders among evolutionary biologists and its own carefully gathered body of evidence sitting quietly behind it. That is where we go next. Charles Darwin himself sat with this exact question for years, and by his own account it frustrated him more than almost anything else in the entire study of human origins. In 1871, publishing The Descent of Man, Darwin devoted real careful attention to the mystery of human hairlessness, and he began, somewhat unusually for him, by ruling things out rather than proposing them. A naturalist named Thomas Belt had suggested that bare skin might simply help people in the tropics rid themselves of ticks and other biting parasites more easily. Darwin considered the idea, weighed it seriously, cited it at length in his own writing, and then set it aside. If losing your fur really did offer that kind of straightforward survival advantage against parasites, he reasoned you would expect to see the same trick show up again and again across the animal kingdom in the countless other tropical mammals facing an identical problem. None of them had bothered. Monkeys, deer, wild pigs, every one of them stayed covered and simply groomed the parasites off by hand or by tongue instead. So Darwin reached for a different explanation entirely, one that had nothing to do with survival and everything to do with attraction. Hairlessness, he proposed, was a secondary sexual trait shaped over countless generations, not because it kept anyone safer or healthier, but because someone somewhere found it appealing and passed that particular preference down the family line, the same way a peacock's tail or a stag's antlers had been shaped by preference rather than pure necessity. He drew a direct comparison to other primates too, noting that several species of monkey display patches of bare, brightly coloured skin, sometimes flushing even more vividly during the breeding season, a pattern he considered a clear, well-documented case of sexual selection, acting directly on skin rather than fur. If it could happen there in full view of any naturalist willing to look, why not in a slower, more thorough version, across an entire ancestral body? He pointed to something that still holds true today as quiet supporting evidence. In every population studied on every continent, women are on average noticeably less hairy than men, exactly the kind of lopsided pattern you would expect from sexual preference, rather than a shared survival pressure that should in principle affect both sexes equally. Have you ever wondered what the public made of an idea this bold coming from the most famous scientist in the world at the time? Not everyone took it well. Within the same year, Darwin's book appeared. An anonymous satirical pamphlet began circulating with the delightfully absurd title, The Fall of Man or the Loves of the Gorillas, imagining a gorilla philosopher lecturing his fellow apes about how humanity had supposedly descended from gorillahood after one particularly persuasive hairless mutant charmed his way into the hearts of every female in the troop. It was billed with tongue firmly in cheek as a popular lecture on Darwinian sexual selection delivered by a learned gorilla, and it captured better than any serious rebuttal just how strange this particular corner of Darwin's theory sounded to ordinary readers hearing it for the first time. Even Darwin's own longtime collaborator Alfred Russel Wallace, the very naturalist who had independently arrived at the theory of natural selection alongside him, publicly disagreed with this particular piece of the argument, finding it difficult to imagine an entire species collectively developing and then maintaining for countless generations such a specific, apparently arbitrary preference. Wallace pointed out reasonably enough that such a fashion would have needed to somehow sweep through every population on Earth, at once persisting with remarkable consistency across thousands of generations, a coordination problem he found almost as puzzling as hairlessness itself. Darwin, in other words, had noticed something real and important about your own body, and reached for an explanation that the scientific community itself could not fully agree on even at the time. The debate he started did not end with him. It simply went quiet for well over a century, waiting for someone to pick it back up with better tools than a 19th century naturalist ever had available. That someone turned out to be a pair of researchers named Mark Pagel and Walter Bodmer working at the University of Reading, who published a short, sharply argued paper in 2003 in the Proceedings of the Royal Society, carrying a title almost daring enough to make you smile on its own. A naked ape would have fewer parasites. Their idea in essence took Darwin's two competing explanations, the practical one he dismissed and the romantic one he kept, and quietly stitched them back together into a single argument rather than treating them as rivals. Hair, they pointed out, is an excellent habitat for exactly the kind of biting blood-feeding parasites capable of spreading serious disease ticks and lice, among them some of which have carried illnesses like typhus through human populations for as long as history has been recorded, moving quietly from host to host, wherever a thick coat offered enough cover to hide in undisturbed. A body with less hair offers these parasites far less cover to hide in, and far fewer places for their eggs to attach securely. That much on its own sounds like straightforward natural selection, exactly the kind of practical survival advantage Darwin had already considered and rejected, on the grounds that no other tropical mammal seemed to need it. Pagel and Bodmer had a ready answer for that particular objection too. Other tropical mammals, they noted, never developed the cultural tools humans eventually did: fire, shelter and clothing, among them tools that let a hairless body survive cold nights and harsh weather, that would otherwise make bare skin a serious liability rather than an advantage. Take away fur and most animals simply die on a cold night. Take away fur from a creature that has already learned to build a shelter and tend a flame, and the calculation changes completely. Here is where Pagel and Bodmer's version differs, and differs cleverly. They proposed that hairlessness did not need to work through only one mechanism at a time, the way Darwin's generation tended to argue in strict either-or terms. A body with visibly less hair would also quite naturally make it easier for a potential mate to actually see the state of the skin underneath spotting, rashes, sores, or an active parasite infestation at a glance, in a way thick fur would have quietly concealed for millions of years. Bare skin on this view became a kind of walking health certificate. Nothing to hide meant quite literally nothing hidden. Once that visibility mattered even slightly to who chose to pair off with whom, sexual selection could step in and accelerate a trend that natural selection had already started pushing hairlessness further and faster than pure survival pressure alone would likely have managed on its own. Two separate forces, pulling in the exact same direction at once, rather than two rival explanations forced to compete for a single correct answer. Would you have guessed before tonight that something as simple as clear skin might once have functioned as an actual advertisement, the evolutionary equivalent of a clean bill of health, displayed for anyone considering you as a partner? There is a certain blunt honesty to the idea once you sit with it. Long before medicine, long before mirrors, Even the surface of a body may have been doing quiet diagnostic work all on its own, visible to anyone willing to look closely enough. No blood test, no physician, no way at all to peer beneath the surface of another creature's body, and yet the surface itself may have been telling anyone paying attention almost everything they actually needed to know. Pagel and Bodmer's paper offered one more piece of supporting evidence worth sitting with, and it takes us back to a creature we already met earlier this evening. The naked mole rat, that small pink nearly hairless rodent tunnelling through the soil of East Africa, lives its entire life at remarkably stable underground temperature, which rules out simple heat regulation as the reason for its own bare skin, since a burrow rarely swings between dangerous extremes the way open grassland does. What that same underground world does offer in abundance is exactly the kind of tight, crowded, parasite-friendly conditions where ectoparasites thrive and spread rapidly, from one tunnel mate to another, packed together in tight, humid passages, with nowhere to retreat from an infestation once it takes hold. A hairless mole rat, just like a hairless human, may simply be harder real estate for a tick or a louse to successfully settle into, and easier for a burrow mate to inspect and groom clean besides. Later researchers picked up this thread and complicated it in a truly interesting way. A study published some years after Pagel and Bodmer's original paper tested something you might not expect. Volunteers were asked to spot a small insect placed on two different patches of skin, one completely bare, freshly shaved, and one covered in the same fine, nearly invisible hairs we spent time with much earlier tonight. The volunteers noticed the insect faster on the lightly haired skin, not the bare patch. Those thin, easily overlooked strands, it turns out, may function less like leftover insulation and more like an early warning system, each one wired to a nerve sensitive enough to flag the faintest unwanted visitor the instant it lands, the same way a spider senses the smallest tremor travelling along a single strand of web. Sit with that particular finding for a moment, because it quietly reshapes the whole picture we have been building tonight. Total, absolute hairlessness may never have actually been the finish line evolution was working toward at all. A body covered in thick, concealing fur hides too much. A body scraped completely clean of every last hair loses a useful alarm system in the process. Somewhere between those two extremes sits exactly what you're wearing right now. Skin bare enough to see clearly yet lightly, furred enough to feel almost anything before it settles in and causes real harm. Evolution, once again, tonight appears to have settled for a careful compromise rather than a clean dramatic extreme, the same pattern we noticed earlier when we discovered your body never actually lost a single follicle at all, only quietly changed what each one was instructed to grow. So the fur did not disappear from your body for one single tidy reason after all, at least according to this particular line of thinking. Thick concealing fur came off because it hid parasites and disease from view, and because it hid the truth of a body's health from anyone deciding whether to build a life alongside it. A thin, nearly invisible layer stayed behind, not as some incomplete leftover of the old coat, but as something closer to a replacement system, entirely trading concealment for detection, trading a hiding place for an alarm bell. There is something worth pausing on here, a small thread that quietly connects almost every serious theory we've examined together tonight. Grooming, the simple act of one primate picking through another's fur searching for exactly these kinds of pests, occupies an enormous amount of time in the daily life of most other primate species, chimpanzees and baboons. Among them, often stretching across hours of every single day, tallied up patiently between individuals who trade the favour back and forth like a kind of social currency. A body needing less of that constant painstaking maintenance would have freed up real time and energy for almost anything else. What your ancestors eventually did with that newly freed time is a story worth its own careful telling, and we're not quite finished setting up all the pieces required to tell it properly. Before we move on, it deserves saying plainly that this particular theory, elegant as it sounds, remains honestly difficult to prove with the same kind of hard physical evidence a fossil or a skeleton can provide. Critics point out that thermoregulation and simple body size, scaling the very forces we spent time with earlier tonight, might already explain most of what needs explaining without requiring parasites or mate preference to do any additional work at all. Human hairiness also varies noticeably between populations in ways that look to some researchers more like ordinary cultural fashion, drifting over time than any deep evolutionary signal shaped as much by climate and clothing habits as by any ancient preference passed down through countless generations of careful mate choice. The honest, unglamorous truth is that Paget and Bodmer offered a compelling, well-reasoned idea, tested as carefully as the available evidence allows and still waiting more than 2 decades later for the kind of definitive confirmation that would let scientists set it down as settled fact rather than an intriguing possibility. Darwin, it turns out, may have been circling the right general neighbourhood back in 1871 even if he never quite found the exact right house on the street. Attraction, health, visibility. All of it tangled up together underneath a question that started tonight with something as simple as a fossil that never fossilized and has slowly grown into something considerably more personal than any of us probably expected a few hours ago. A 19th century naturalist working with nothing more than careful observation and a stubborn refusal to accept easy answers managed to point roughly in the right direction, using little more than his own eyes, and a great deal of patience long before anyone had the tools to prove him even partly right. There is one more piece of this puzzle left, and it may be the strangest one yet because it does not sit inside a fossil bed or a distant research paper, or even in adult skin at all. It begins quite literally before you were even born, wrapped around a body that had not yet taken its first breath, in a place no textbook chapter on hairlessness usually thinks to look. Every single one of you listening tonight passed through this stage once, without a single memory of it, and the evidence, strange as it sounds, was written directly onto your own skin for a few brief months before quietly disappearing again. That is where we go next. Somewhere around the 13th week of pregnancy, quietly, without any fanfare at all, every single human fetus on the planet begins growing a full coat of hair. Not a few stray strands here and there, complete soft, almost invisible covering spreading steadily from the eyebrows and upper lip downward across the entire body, following the same head-to-toe pattern. Nature seems to favour for laying down hair in general, moving down across the shoulders, the back, the small of the spine, all the way to the soles of the feet, skipping only the palms, the lips, and a handful of other spots that never seem to grow hair at any stage of anyone's life. By the time this process finishes, somewhere around 18 or 20 weeks along, a developing baby is for a brief and strange window of time covered almost as thoroughly as any other primate on Earth. Doctors call this fine, unpigmented hair lanugo, borrowed from the Latin word for wool, and it is worth sitting with the plain fact of it for a moment before we go any further. You wore this coat once. Every person you have ever met wore it too for a handful of months, inside a place none of you remember. Have you ever pictured what you actually looked like at that stage, tucked away somewhere your own mother's ribs, months before anyone had chosen a name for you? Almost certainly not covered in the smooth bare skin most baby photographs suggest. Something considerably closer to the coat we spent our first hour together discussing tonight. It's a strange thing to sit with late at night, that the tidy hairless image most of us carry around of our own earliest selves is not actually accurate at all. So why would a body build something this elaborate only to quietly take it apart again before anyone ever gets to meet the finished result? The honest answer involves a second substance most people have heard of only in passing, if at all. Around the same time lanugo begins growing, the fetal skin also starts producing a thick, waxy, almost cheese-like coating called vernix caseosa, a protective layer built to shield delicate developing skin from a problem most people never think to consider. For the better part of a year, that skin sits completely submerged in amniotic fluid, A warm bath containing exactly the kind of waste products urea among them that would slowly damage and wrinkle unprotected skin over so many months of constant exposure. The same way skin left too long in bath water starts to soften and pucker within a single afternoon, except stretched across the better part of a year instead. Vernix solves that problem. Lanugo, remarkably, is what keeps the vernix actually in place, each tiny hair acting as a physical anchor point, gripping the waxy coating and holding it against the skin the way a rough surface holds paint far better than a smooth one ever could. Without that anchor, researchers studying fetal development believe the vernix would simply slide free, leaving weeks of delicate developing skin with no protection at all during exactly the stretch of pregnancy when it needs that protection most. Remove the lanugo too early, in other words, and the whole protective system built around it would simply slide away. Nature once again tonight appears to have built two separate pieces of a single working system, timed to arrive and depart together, neither one doing its full job without the other quietly holding it in place. There is something almost touching about that particular piece of biology, if you allow yourself to sit with it for a moment. Before you could see, before you could hear anything beyond a muffled heartbeat, before you had any awareness of your own existence at all, your body had already quietly engineered its own temporary protective coat built and discarded on a precise schedule, entirely without your involvement or knowledge. No decision was made. No conscious plan was drawn up anywhere. A body simply did on its own exactly what needed doing, the same quiet competence it has been demonstrating all night long, from follicle counts to sweat glands, to the careful timing of a coat nobody ever consciously chose to grow. Modern imaging has actually let researchers watch a version of this process unfold in real time rather than relying only on samples collected after birth. Ultrasound studies conducted across ordinary pregnancies have tracked the general timeline of skin and hair development stage by stage, confirming what earlier generations of embryologists had only been able to piece together secondhand from stillbirths and miscarried pregnancies studied out of medical necessity rather than convenient observation. Today, expectant parents occasionally catch a faint, fuzzy hint of this hidden coat on a routine scan without ever fully realizing what they are looking at. One more, small, mostly invisible detail folded into an experience already overflowing with far more dramatic things to notice. By around the 33rd or 36th week of pregnancy, most of that lanugo has already done its job and started to disappear directly into the surrounding amniotic fluid, rather than falling away and vanishing somewhere unseen. And here is a detail that tends to truly surprise people the first time they hear it. That shed hair does not simply dissolve, it becomes part of what a fetus swallows, along with the fluid itself, eventually contributing to the very first substance to pass through a newborn's body. After birth, the dark, tarry first stool doctors call meconium. You quite literally consumed your own temporary coat before you ever took a single breath of open air. Would you have guessed before tonight that something this strange and specific was happening to every single person? At some point long before any of you were old enough to remember it, not every baby finishes shedding on schedule. Roughly 3 in 10 newborns still arrive with visible patches of lanugo remaining especially across the shoulders, back and forehead, a pattern seen more often in babies born a little early before the usual shedding window is fully wrapped up. Doctors seeing this consider it normal, unremarkable variation, rather than any cause for concern, and the remaining hair typically finishes falling away naturally within the first few weeks of life, quietly replaced by the same fine, nearly invisible vellus hair we spent time with earlier this evening, the exact same soft covering that continues standing guard over your own skin at this very moment. Generations of new parents, long before anyone understood the biology behind it, noticed this same soft down on their own newborns and simply folded it into the ordinary unremarkable texture of early parenthood, One more small detail among the countless others that come with holding a brand new person for the very first time. Here is where the story takes an unexpected turn, because lanugo, it turns out, is not always confined strictly to before birth. In rare cases, adults can develop something resembling it again later in life, and the reasons behind that reversal deserve to be handled with real care rather than curiosity alone. Among certain serious eating disorders, when a body's fat reserves drop critically low, skin can respond by growing this same fine, soft hair as an improvised attempt at insulation, compensating in the only way it still can for warmth, normally provided by the fat lying just beneath the surface. Physicians who work with patients recovering from these conditions consider it one of many quiet physical signals a struggling body sends out worth noticing with compassion rather than alarm. It is a sobering reminder of how deeply your body still remembers this particular fallback option, even now waiting quietly in reserve for circumstances none of us would ever wish on another person. If anything about that thought sits heavily with you tonight or with someone you love, know that real support exists, gentle and immediate whenever it is needed. A different, considerably rarer condition offers a gentler note to end this part of tonight's story on, and it takes us back several centuries to the court of a French king, where a very different kind of lifelong hair told a very different kind of story altogether. In the middle of the 1500s, a young man named Pedro González arrived at the court of Henry II of France, having been born on the island of Tenerife with a striking and unusual trait. His entire body and much of his face were covered in thick, soft hair, a lifelong condition doctors would only much later come to call hypertrichosis. Brought to the French court as a child and initially treated as little more than an oddity for the amusement of others, González gradually won something far more meaningful than mere curiosity. He was given a genuine education learning Latin well enough to converse fluently with visiting scholars and study the classical texts. Every educated nobleman of his era was expected to know, and he earned a reputation less for his appearance than for his evident intelligence, courtesy and bearing. Contemporary chroniclers and the noble households that later welcomed him and his family across France and Italy gave him a Latinized name history remembers him by today, Petrus Gonsalvus. He went on to marry, raise a family, and spend his years moving between some of the most influential courts in Europe, respected in circles that, in an earlier century, might easily have shown him nothing but cruelty instead. Visitors who came expecting to gawk at a curiosity often left, according to surviving accounts, describing instead a thoughtful, widely educated gentleman who simply happened to look different from everyone else in the room. Several of his own children inherited the same striking trait, a detail that fascinated the doctors and naturalists of the era, long before anyone had the faintest idea what a gene actually was, and portraits of the family painted by artists invited specifically to capture their unusual appearance still survive in museum collections today. Quiet, dignified witnesses to a family history stretching back nearly 5 centuries. Historians studying the era note that the family story carried an unusual double life even at the time, treated in some rooms as a marvel to be gawked at and in others as simply a family belonging, unusual as it was to the ordinary business of court life, marrying, raising children, growing old. Modern genetics has since offered a real answer to a mystery that once seemed almost magical. Conditions like the one Gonsalvus carried appear to involve the same broad category of genetic machinery we spent time exploring a little earlier tonight, the very switches responsible for turning hair follicles on or off across the body. In most people, many of those old instructions for a full thick coat sit quietly deactivated the way we discovered earlier this evening. In someone with hypertrichosis, it appears a small number of those same switches simply failed to receive the signal to power down, leaving old instructions running, that nearly everyone else quietly finished their work centuries upon centuries ago. Nothing foreign was added to Gonsalvus or his children. Nothing extra had to evolve, appear, or mutate into existence from scratch. an old file present in every human genome without exception, simply stayed open a little longer than it does in the rest of us. So the coat, it turns out, was never entirely gone from any of us, not even for a single generation. It surfaces briefly and universally before birth, anchoring a protective coating no developing body could safely do without. It occasionally resurfaces later in rare and specific circumstances as a strange, unmistakable echo of the very same instructions living quietly inside every one of us, waiting patient and dormant the way a pilot light waits behind a stove long after the last time anyone actually needed it lit. Hours into tonight's story now, and the fur your ancestors supposedly lost so long ago keeps turning out to be remarkably difficult to fully misplace. Think back for a moment across everything this particular thread has touched tonight. A follicle count nearly identical to a chimpanzee's, a genetic instruction manual switched off in 9 unrelated species without ever being deleted. Now an entire coat grown and shared on schedule inside every single person who has ever been born. The pattern repeating itself again and again throughout tonight's story is not one of loss, at all not really. It is a pattern of things being quietly, carefully hidden away, rather than thrown out, kept near at hand by a body that seems on some level reluctant to ever fully let go of what it once was. Which raises one more question worth carrying into the next stretch of tonight's journey. If the instructions for a full coat are still sitting there largely intact, ready to be triggered under just the right circumstances, why did evolution leave a small handful of places on your body permanently exempt from ever losing their hair in the first place? Your scalp, your eyebrows, a few other quiet corners nature seems to have deliberately chosen to protect long after it stripped away almost everything else. Every theory we have gathered so far tonight has explained an absence, heat needing somewhere to escape, parasites needing somewhere to lose their grip, water needing somewhere to evaporate freely. None of them so far has fully explained the opposite question, the handful of places your body seems to have gone out of its way to keep covered deliberately stubbornly, for reasons every bit as old as the rest of tonight's story. Something protected those particular patches of skin from every single pressure we have discussed tonight generation after generation, while the rest of the body gave way completely. That is where we go next. Look in a mirror tonight if one happens to be nearby and count the places fur actually held its ground. Your scalp, your eyebrows, your eyelashes, a modest patch under each arm and another lower down. Almost everywhere else the coat thinned down to something barely worth mentioning, exactly the transformation we have spent this entire evening trying to understand. In these particular spots, though, it stayed thick, dark, and unmistakably present, as though something had drawn a careful line around each one and simply refused to let the rest of tonight's story apply there. None of that was an accident, and none of it happened for the same reason twice. 5 separate patches of skin, 4 separate stories, each one waiting patiently on your own body for someone to finally ask why. Start at the top since it is the most visible holdout of all. Scientists studying human evolution have long suspected that scalp hair survives for reasons closely tied to something we spent real time with earlier tonight. The delicate, energy-hungry brain sitting directly beneath it. It was for decades more of an educated guess than a properly tested claim, the kind of idea that sounds reasonable enough to repeat in a lecture hall without anyone quite getting around to checking it under controlled conditions. In 2023, researchers from Loughborough University in England and Penn State in the United States decided to test that old suspicion properly, rather than simply theorizing about it from an armchair. Professor George Havenith and his colleagues built what is called a thermal mannequin, essentially a life-sized model rigged with internal sensors capable of measuring heat gain and loss with real precision, then fitted it with a series of human hair wigs ranging from perfectly straight to tightly curled. Have you ever wondered whether the shape of a single strand of hair could actually matter on its own for something as serious as protecting a brain from overheating? According to the results, it does, and rather dramatically. Every wig tested reduced the amount of solar heat reaching the scalp compared with bare skin but tightly curled hair performed best of all, creating a springy air-filled layer that blocked far more radiant heat than straight hair. Managed all while requiring noticeably less sweating underneath to keep the head at a safe, stable temperature. Straight hair, by comparison, tended to lie flatter against the scalp, once even slightly damp, losing much of that protective loft exactly when a body needed it most. Professor Nina Jablonski, whose work on skin has come up once or twice already tonight, helped guide the research, framing the scalp as a kind of specialized exception, built to solve a very particular problem. The rest of the body could afford to trade insulation for evaporative cooling. The scalp, sitting directly above an organ that cannot tolerate overheating, even briefly seems to have needed a gentler, passive kind of shield, instead one that let the brain stay cool without demanding a constant, expensive supply of sweat just to manage a single square foot of skin. So while the rest of your body was busy giving up its coat for reasons we spent hours unpacking earlier tonight, your scalp appears to have quietly struck a different bargain, keeping just enough shade overhead to spare the most demanding organ in your entire body from paying that particular cost. Every time sunlight lands on your own hair, rather than directly on bare skin, some faint echo of that ancient trade is still quietly playing out, whether or not anyone standing nearby happens to notice it. Move down slightly and the story changes completely. Eyebrows have almost nothing to do with heat and everything to do with something considerably more social. In 2018, researchers at the University of York, led by an anatomist named Paul O'Higgins, alongside archaeologist Penny Spickins, turned their attention to a heavy jutting ridge of bone found on the skulls of archaic humans, a feature strikingly absent from anyone you might pass on the street today. Working from a fossil skull known as Kabwe 1, discovered decades earlier in what is now Zambia, and belonging to a species that lived several 100,000 years ago, the team built a detailed three-dimensional model and tested it against every practical explanation anyone had previously proposed. Did the heavy brow ridge help distribute the force of biting and chewing? Did it simply fill leftover space where a flatter, more rounded skull would otherwise have left a gap? Their modelling ruled out both ideas fairly conclusively, using software originally built for engineering rather than anthropology to simulate exactly how stress travelled across the skull with and without the ridge in place. Removing the ridge from their simulation changed almost nothing about how the skull handled the mechanical stress of eating. What the ridge did resemble, the researchers argued, was something closer to a permanent billboard, not unlike the colourful, swollen patches of skin certain male primates display today as a fixed, unmistakable signal of dominance. Look at a mandrill, one of the researchers pointed out, and you find bright ridged swellings on either side of the muzzle, grown under the influence of hormones and impossible to hide or soften. Ancient human faces may have carried something functionally similar, a permanent bony announcement rather than a passing expression. As human faces gradually flattened over the following hundreds of thousands of years, that fixed billboard gave way to something far more flexible, sitting in roughly the same spot, a thinner ridge of hair capable of lifting, dropping, arching and furrowing in a fraction of a second. A single raised eyebrow can now signal surprise. A lowered pair can signal doubt or concentration. None of that nuance was available to an ancestor stuck wearing a fixed, immovable slab of bone in the same location. Would you have guessed before tonight that something as small as an eyebrow might once have replaced an entire piece of skull, simply because moving parts turned out to be more socially useful than permanent unmoving ones? It is a strange trade to imagine in reverse trading. Solid bone for a thin strip of muscle and hair. And yet that particular trade appears to have paid off handsomely, generation after generation, for a species that increasingly depended on cooperation with total strangers to survive at all. As human groups grew larger and cooperating with unfamiliar faces became increasingly essential to survival, that small, expressive strip of hair may have quietly become one of the more valuable pieces of equipment sitting on the entire human body allowing recognition, sympathy, and warning to travel between two people without either one needing to say a single word. Just below the eyebrow sits another surviving patch with its own separate, entirely mechanical explanation. In 2015, a team of engineers at the Georgia Institute of Technology, led by David Hu and a graduate student named Guillermo Amador, set out to answer a question that had somehow gone unresolved for a remarkably long time. What are eyelashes actually for? After measuring the eyes and lashes of 22 different mammal species borrowed from preserved specimens at a natural history museum, the team built a small enclosed tunnel to test airflow and constructed an artificial eye to test how air behaved around lashes of varying length. Across every single species measured from humans down to hedgehogs, the ratio held remarkably steady. Eyelash length consistently measured near 1/3 the width of the eye itself, no matter how large or small the eye happened to be. That particular ratio the experiment showed was not a coincidence. Lashes shorter than that ideal length did little to slow the air moving across the surface of the eye. Lashes noticeably longer actually made things worse, channeling incoming air directly toward the eye rather than deflecting it, and speeding up exactly the kind of evaporation and dust deposition a longer lash might seem at first glance better equipped to prevent, sitting at precisely 1/3 of the eye's width. Though lashes created a slow, gentle cushion of still air directly above the surface, keeping the eye moist for longer and steering the bulk of airborne dust safely around it instead of straight into it. Only one animal in the entire survey broke the pattern outright. Elephants with their famously long lashes turned out to be an exception the researchers still find deeply puzzling, a reminder that even a rule holding steady across 21 other species can still meet its one stubborn holdout. So even something as small and often overlooked as an eyelash turns out to be operating according to precise testable physics, tuned by evolution to a ratio so consistent that measuring an animal's eye alone lets a researcher predict its lash length almost exactly. That leaves two final patches worth mentioning before we wrap up this particular chapter of tonight's story, tucked beneath the arms and lower on the body, and both trace back to a kind of sweat gland we have not yet properly discussed tonight. Unlike the thin, watery eccrine glands responsible for the cooling system we spent considerable time with earlier this evening, these particular glands, called apocrine glands, produce a thicker protein, rich secretion, largely odorless the moment it reaches the surface of the skin, until local bacteria get to work, breaking it down into the more distinctive scent most people associate with these particular regions of the body. These same glands sit dormant through most of childhood, only becoming active once puberty begins arriving on the same rough schedule as the coarser, darker hair growing in around them, as though both systems were quietly switched on together by the very same signal. Many researchers studying this pattern believe the surrounding hair exists partly to trap and slowly release that scent, turning a simple biological byproduct into a signal capable of traveling further and lingering longer than bare skin alone could ever manage on its own. A quieter, more intimate echo of the kind of scent-based communication still fairly common across the wider mammal world. It is worth remembering too something we touched on a little earlier tonight regarding parasites. Concentrated patches of hair also happen to concentrate exactly the kind of habitat certain biting insects still prefer, which may be one small reason these particular regions never fully join the rest of the body in going bare. There is a modest, honest hedge worth adding here in fairness to the actual state of the science. Exactly how much genuine information human body scent carries, and how much attention any of us actually pay to it without realizing it, remains a livelier and less settled question among researchers than some popular articles tend to suggest. Some studies claim measurable effects on attraction or mood. Others find the evidence considerably weaker once modern perfume soaps and daily washing habits are factored into the picture, all of which strip away most of the natural scent this system was originally built to carry. What is not seriously disputed is the anatomy itself. These two regions carry a noticeably higher concentration of apocrine glands than almost anywhere else on the body, and the hair covering them lines up with that concentration a little too precisely to write off as pure coincidence. So here gathered together at last sits a small specific map of your own body, a scalp shielding a brain that cannot afford to overheat, eyebrows carrying messages a jaw of solid bone never could, eyelashes tuned by simple physics to one exact universal ratio, and two final patches quietly built around scent rather than heat or sight at all. Every square inch of you tonight, it turns out, ended up exactly the way it is for a reason even the parts most people never once think to ask about. Notice too how differently each of these 5 stories actually unfolded. One came from a laboratory in England built around a mannequin and a stack of wigs. One came from a fossil skull excavated decades ago and pieced together digitally. One came from a small enclosed tunnel, rigged to test moving air, built specifically to answer a single oddly specific question about eyelashes. One rests on evidence still being gathered and debated even now. 4 different research teams working in 4 different decades, using 4 completely different sets of tools, all quietly converging on the same conclusion this evening, happens to be built around. Nothing about your body is arbitrary, even the parts easiest to take entirely for granted. Have you ever walked past a mirror, caught sight of your own eyebrows or the fine hair on your own arm and thought of any of it as leftover or accidental or simply there for no particular reason at all? Most people do most days without a second thought. Tonight, hopefully, that particular habit feels a little harder to fall back into. There is one thread left hanging, though, and it may be the most personal one of all. Losing that thick all-over coat did not simply change how your body handles heat, or water, or sunlight. It changed how you connect with other people in a way that reaches all the way from the quiet grooming rituals still practiced by every other primate on Earth, down to something happening on your own skin at this very moment, whether you have noticed it tonight or not. That is where we go next. Every other primate on Earth still spends a startling portion of its day doing something you have probably not done in the literal sense since you were far too young to remember it, sitting quietly beside another member of its own group, working carefully through fur strand by strand, picking out debris and insects with patient, deliberate fingers, in a ritual that can stretch on uninterrupted for the better part of an hour, between 2 individuals who trust each other completely. Watch a troop of baboons or chimpanzees for more than a few minutes and you will see it everywhere, one animal settling into another's lap, eyes half shut, utterly relaxed, while a companion combs steadily through its coat. It looks, and in a very real sense actually is an act of simple hygiene. It is also researchers have come to understand something considerably deeper than that. Studies measuring stress hormones in groomed primates have found levels dropping noticeably during and after a session, the same kind of physiological calm you might associate with a long unhurried hug between 2 people who trust each other completely. The animal being groomed is not merely getting cleaner, it is in a very real sense being told wordlessly and at length that it belongs. An Oxford anthropologist named Robin Dunbar spent years studying exactly what grooming does for primates beyond the obvious working through data, gathered across dozens of different species living in dozens of different sized groups. What he found was that time spent grooming tracks closely with group size rising steadily, as larger and larger groups require more relationships to be quietly maintained. Push a group up toward 200 individuals, Dunbar calculated, and the math turns almost absurd. Members would need to spend more than half of every single day grooming one another just to maintain the web of trust and alliance holding that group together, leaving barely any time left over for the actual business of finding food and staying alive. No primate group of that size relying purely on physical grooming could realistically survive its own social arithmetic. Have you ever wondered how your own ancestors managed to survive in groups considerably larger than that without spending most of daylight combing through each other's hair? Dunbar's answer, laid out across decades of careful research, was as elegant as it was unexpected. Once the fur itself began thinning out, the old currency of physical grooming became considerably harder to spend. Something had to step in to take its place, some way of maintaining trust and closeness between far more people than any single pair of hands could ever hope to groom directly. Dunbar's proposal was language itself, arriving not primarily as a tool for describing the world, but as a faster, more efficient substitute for exactly the bonding grooming used to provide. A conversation, unlike a grooming session, can reach several people at once. It travels across a room instead of requiring skin-to-skin contact. It lets you learn who can be trusted, who recently fought with whom, and who just became a parent, all without ever laying a single finger on another person. Dunbar even pointed to a rough number worth sitting with tonight, a ceiling of roughly 150 stable relationships that keep showing up again and again in hunter-gatherer communities in traditional villages, even in the address books and contact lists of people living in cities today, as though some ancient limit on genuine closeness never entirely left us, no matter how the tools for maintaining it have changed. Gossip, in other words, in the broadest and least judgmental sense of that word, may be one of the oldest inheritances sitting quietly behind every single conversation you've ever had. The same impulse that once sent a chimpanzee's fingers combing through a friend's fur may be the very same impulse currently keeping you here tucked in, listening to one long, unhurried voice telling you a story before sleep. Every late-night phone call with an old friend, every quiet exchange of small, unremarkable news between two people who care about each other, may be doing exactly the same ancient work that hands once did, simply dressed up now in the sound of a voice instead of the touch of fingers through fur. There is something worth sitting with in that thought for a moment, especially tonight of all nights. The coat disappeared. The need it used to satisfy did not disappear along with it. It simply found an entirely new place to settle in words instead of fingertips in stories, instead of strokes through fur in exactly the kind of quiet, one-sided conversation happening between us right now. Which brings us at last to one final small detail. This entire story has been quietly circling since the very first moment we sat down together this evening. Reach up gently and touch your own forearm if you would like to. Somewhere beneath your fingertips, attached to nearly every hair follicle still remaining on your body, sits a tiny, easily overlooked muscle called the erector pili. Its only job, inherited from an ancestor wrapped in considerably more fur than you carry tonight, is to contract on command, pulling each individual hair upright the instant your nervous system decides the moment calls for it. Doctors have known the muscle by name for well over a century, tucked away in anatomy textbooks, under a heading most people never think to open, and yet almost nobody outside of medicine has ever paused to wonder what it is actually for or why it still bothers firing at all. Cold air brushing across bare skin can trigger it. So can fear arriving suddenly out of nowhere. So strangely enough can a single perfect swell of music at exactly the right moment in a favourite song, a phenomenon researchers studying the effect have taken to calling simply chills. You have felt this 1,000 times, almost certainly without ever once putting a name to it. That faint prickling wave rising across your arms or the back of your neck. Small raised bumps appearing briefly on skin that only a moment earlier looked completely smooth. This particular reflex, researchers have found, tends to arrive along two rather different roads. One kind shows up out of nowhere, unbidden, tied to sudden cold, or a flash of fear, part of a threat detection system old enough to have served every furred ancestor you've ever had. The other kind, the kind stirred by a swelling chorus, or a perfectly placed key change in a favourite song, appears to travel through an entirely different route, in the brain, tangled up with reward and dopamine rather than danger-proof, that this ancient reflex has at some point along the way been quietly repurposed for beauty as much as for fear. In a fully furred ancestor, this same reflex actually accomplished something. Raising every hair on the body trapped a thicker layer of warming air against the skin on a cold night, and made a frightened or threatened animal look noticeably larger and more intimidating to whatever had startled it. The exact same trick a cat still performs when its fur puffs out along an arched back. On you tonight with almost nothing left, standing behind each follicle to actually lift the reflex fires anyway, faithfully for no practical reason at all beyond simple habit. Scientists who study this phenomenon closely have even found something quietly poignant hiding inside the data. A recent study tracking the reflex across repeated exposure to the very same emotional trigger found that the feeling itself, the reported sense of chills or being moved, tends to fade a little, with each repetition the way any strong emotion naturally dulls with familiarity. The muscle, though, kept firing anyway, contracting just as reliably on the 10th exposure as it had on the first, almost entirely detached from whether the person attached to it still felt anything at all, as though the muscle remembers the instruction long after the rest of you has moved on to something else quietly loyal to a body plan that stopped needing it millions of years ago. Would you have guessed, sitting down at the very beginning of this story several hours ago now, that it would end here with a small, mostly useless muscle, quietly proving better than any fossil or gene ever could that the coat was never entirely gone at all? It seems a strange place to land, and yet it feels somehow exactly right, a fittingly small and personal note to end on after everything this evening has covered. Think back for a moment across the whole shape of tonight's journey, because it has taken us somewhere further than any of us probably expected when we first sat down together. A scientist in a quiet laboratory outside Boston counting follicles under a microscope, and finding a number nearly identical to a chimpanzee's and a British zoologist decades earlier, who first dared to call us the naked ape in public. A peat bog in Denmark, a frozen mammoth in Siberia, a dinosaur pulled from a Canadian mine, each one teaching us why your own ancestors left behind no trace of their fur at all. A small, unglamorous insect quietly keeping a clock on human skin for longer than anyone thought to ask, and another cousin louse borrowed strangely enough from a gorilla. A sweat-soaked hunter in the Kalahari chasing an antelope for hours under a brutal sun, and a runner in the Welsh countryside outpacing a horse on the hottest day of the year. A photograph of a scale model, tracking sunlight across an open savanna, later corrected and refined by scientists unafraid to admit the first version had been too simple. 9 unrelated animals reaching for the exact same handful of genes without ever knowing it. An elephant's ear doing the work no sweat gland ever could, and a mineshaft thought experiment that explained why. A century-old idea about swimming apes tested honestly, and found wanting even as a gentler version of it quietly survived the scrutiny. A Victorian naturalist circling the right answer without ever quite landing on it, mocked in his own lifetime for trying. A baby wrapped in a coat it would shed before it ever took a breath, and a hairy gentleman in a French court who carried that same coat for an entire lifetime instead. A scalp, a pair of eyebrows, a set of lashes, each one keeping its place on your body for a reason entirely its own. And now, finally, a single small muscle, still faithfully raising hairs that mostly are not there anymore simply because nobody ever told it to stop. None of it was ever really about hair, not entirely. It was about a body that adapted layer by layer, decision by decision across millions of years, until it became exactly the body carrying you through this evening right now. Every theory we examined tonight got a piece of the story right. Almost none of them on their own told the whole truth. The real answer, the one this entire night has been quietly building toward, was always going to be larger and messier than any single explanation could hold, which is very often how the truth about deep old questions tends to work out. Heat-water geography, genetics, parasites, attraction, even a scrap of soft coat you wore once before birth and never entirely put away. all of it true all at once, layered on top of itself the way sediment settles slowly at the bottom of an old lake. So here you are at the end of it, sitting somewhere in the dark skin, bare heart, steady carrying inside your own body, a complete silent record of everything we've spent this evening uncovering together. A coat you no longer wear but never quite lost. A cooling system built for chasing things across open ground. A handful of patches nature refused to give up. A muscle still standing at attention for a threat that stopped mattering millions of years ago. You're in the quietest and most literal sense possible, a walking museum of your own deep past, carrying every exhibit from tonight's story on your skin without ever needing to visit a single building to see it. Every scientist, every researcher, every quietly stubborn theory we sat with tonight was really just trying to answer one small, deeply human question, the same one that probably brought you here in the first place. What am I actually underneath everything I assume about myself without ever stopping to check? Thank you truly for spending this stretch of your evening here, letting this particular story fill the quiet hours before sleep finally arrives. There is something quietly special about being trusted with someone's last waking hour of the day, a responsibility this story has tried to honor with real care at every step along the way. Stories like this one take real care to put together hours spent chasing down the right studies, the right names, the right small true details, all in the hope that somewhere along the way tonight something in it reached you the way it was meant to. If any part of tonight settled into you the right way, sat with you a while, or simply gave your mind somewhere gentle to rest, then this story did exactly what it set out to do. There is always another one waiting, another quiet corner of history or biology, or the strange overlooked details of your own body ready whenever you are ready to hear it. Rest well tonight. Let your eyes settle shut, let this voice fade into the background, and let whatever is left of that ancient coat, invisible as it now is, faint as it now is, keep you just a little warmer until morning.